Está preparando la retransmisión.
Ok.
Debería poder compartir en un minuto.
Me dices apenas lo envíes.
Acabo
¿Me
de enviarte
escuchas
el
bien?
correo. Ujú. Acabo de enviarte el correo.
¿Al Gmail o al otro?
Respondiendo al correo que me enviaste.
Ah,
Ujú.
ok. No me llega nada. Ah, ya. Wait. 31. Ta, 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 ta. Me escribes apenas te llegue, porfis.
Listo.
Listo. Listo. También ya estoy aquí en el live.
Yo intenté escribir algo para ver si, para intentar borrarlo en el YouTube,
¿Pudiste escribir
pero
algo?
pues sí, lo pude borrar, que me interesa saber si puedo borrar, pero pues fui algo que yo misma escribí, entonces no sé si tiene sentido.
Espérate, yo escribo y tú borras.
Dale, por favor, gracias.
Listo.
Ujú.
Ahí
Estamos en,
escribí hello.
estamos
Sí,
en
lo
streaming,
pude
¿no?
borrar.
Ok,
Ujú.
Ujú. Estamos en streaming.
listo. Sí, puede.
Estamos en streaming.
¿Me ven?
Veo tu cámara. Veo tu cámara. Solo requiero, solo requiero estar pendiente cuando se conecte Claire. Te enviaste el correo, ¿cierto?
Sí, ya lo envié.
Listo. Voy a quitar la cámara solo un momentico. Hay algo que podemos hacer en el medio y es poner el link de YouTube en la página, ¿cierto?
¿Ustedes ven mi cámara?
Yo veo tu cámara.
Tu cámara está abierta, sí.
Ya, listo, ya. Espérate, comparto el link por... Ya lo comparto. Por LinkedIn y por Instagram.
LinkedIn, Instagram. Voy a compartir el link en la página. Ir finalizando en 1:34.
Ujú.
Listo.
Hasta el momento solamente se ve la página web compartida, ¿cierto?
Sí,
Listo. Compartido por Instagram ya.
Listo.
eso es lo que vamos a compartir, Duan, eh, la página del evento. O sea,
Sí,
ok.
podemos compartir la página del evento.
¿Les llegó el correo?
Ujú. Sí. ICMAM 2026, Day 2, Comprehensive Live Stream. Ujú. Voy a abrir el link solamente para verificar que funciona.
Me llegó
Ujú.
tu correo.
Sí, funciona.
Listo.
Ujú.
Perfecto.
Le enviaste ese correo es con copia a todos los participantes, ¿cierto?
Sí, sí, sí.
Ujú. Listo. Pedro tiene acceso a todos tienen Pedro tiene acceso al link de Zoom. Ujú. Muy bien.
Comienzo a grabar aquí por Zoom
Dale.
cuando todavía no. Voy a esperar un ratico cuando ingresen.
Listo.
Falta solo el del LinkedIn.
Ujú. Muy bien. Listo. 24 personas mirando en este momento, o sea que sí funcionó la estrategia.
Ok,
Wow.
¿Listo?
perfecto.
24 personas mirando.
Sí, lo compartí en,
Wow.
en, en Instagram.
Ya está
Ujú.
Instagram.
Ya está Instagram, ya va LinkedIn.
Voy a admitir a la profesora Claire Boisson,
Sí, ya la saludo.
haciendo cojos a la profesora Claire Boisson.
Ujú.
Hello,
Andrea.
Hello, Professor Claire.
nice to meet you.
Nice to meet you. So, thank you very much for being here with us today.
No, I am happy to give this talk and thank you for the invitation.
Thank you. Professor, would you like to share your screen? Maybe we
Uh,
can
Sure,
start
sure.
fixing.
Sure, so maybe let me first open the file.
Yeah,
This
great.
is a Beamer presentation. Where is it? Yeah. Okay. Okay. No. So maybe I first have to, yeah. Okay. Yes, and then uh, maybe it's better if I do this. Okay.
Well, well, yes, perfect. Thank you very much. I can see it now.
Okay, so I think it's fine. So it's a 1 hour talk.
Yes, it's 1 hour talk with the questions and yeah, it's 1 hour in total. Yeah.
Or yeah, so maybe it's better if I stop after 55 minutes or?
Yes, yeah, I think it would be okay. And then after the last 5 minutes, we can just open to questions. And
Okay, okay. So I'll try to remember that.
yeah, don't worry. If you need to something, just let me know. I can also tell you. Just
I hope it will be fine. So just check that everything is fine. So you see the whole
yes,
slide? Yeah, yeah.
yes, I can see the slides moving. Yeah.
Just to make sure that everything is there.
Yes.
Maybe I won't be able to go to until the end. That's not very important, I think. Okay, that's the end. Probably it's too long, but one never knows.
Can I ask you something really quick?
Yeah, sure, sure, sure.
Because I would like to confirm, how can I say your name? It's Claire Poisson.
Yes, voisin.
Ouais, vraiment. Oh, merci.
No, but you can say it. You can say it as you want.
But I wanted to have it correctly, you know. Okay,
It is
not perfect, but
normally it's Claire voisin.
Claire
No
Poisson.
voisin.
Ah
But it's
ouais.
not very important.
Okay.
Just do as you like.
Yeah. Okay, Professor. Are you in Paris at the moment?
No, no, I am in the south of France. I was in Paris
Oh,
until yesterday. It was awful.
it's hot, eh?
Yeah, no, it has been dramatic. Yeah.
Yeah, yeah.
We don't have air conditioning in Paris, and
Yes.
it was simply terrible in the bedroom. We were sleeping at 34 degrees at
Mm,
night.
yeah,
That
yeah.
was horrible.
Yeah.
But,
Yeah, the houses here are designed for winter, but not for summer.
yeah.
Yeah, that's true.
Curiously, it is not so warm in the south of France. So.
I would think it was the opposite in
No,
the
no,
south.
normally it's very hot
Yeah, okay.
in summer, but because of this year is very special, and indeed it was warmer in the center and the north of the
Ah,
France.
yeah, okay. So it's moving like because I saw this cloud of heat and it's moving like a
Yeah,
line up to the north,
absolutely.
right? It's something super
Absolutely, yeah.
strange, actually.
From the yes, absolutely. Some
Yeah.
some areas that are absolutely not used with warm weather, like Bretagne or Normandy. They discover what is hot weather. It's very new for them.
Yes. Yeah, I have some friends, they told me they love summer, and I was like, well, because you go there for just 4 or 5 days and you come back. But if you live in the heat,
Absolutely.
it's different.
No, no. Mm. Oh, no, that was terrible in Paris. Sometimes you feel you are in danger because you feel what am I going to do if if it becomes warmer?
Mm.
You are already at the limit, and
Yes, yesterday we were with Professor Shapiro,
I
uh,
know. Yeah.
and he
Mm.
was not in Paris during the weekend, and he came to Paris just for the talk. And he
Mm.
told us like it's too hot there, so he just went for the talk and go
I
back
can
somewhere
imagine.
else.
Yeah.
So that's why I was asking if you were in Paris because then yeah, it's too hot. Yeah. Ah, but nice, nice, nice. Okay. Okay, we will start, Professor, in 7 minutes, and probably we will wait
Sure.
1 or 2 minutes, then we can start. Yeah, okay.
Sorry, I just have some water.
Ah, So I think, Professor, in the meantime, I can introduce you to Karina Navarro. She is the president of our ICMAM organization. Yes, so Karina, maybe you want to.
Hello, Professora. It's my pleasure.
Nice to
She's
meet you.
here with you.
Yeah.
Yeah, nice to meet you.
And we also have Duan Cardona here.
Mm.
Hi, Professor Wasan. Nice to meet you. It's
Hello,
really our great honor.
thank you, it's very kind. I like to give talks, so
Oh, really?
the pleasure is for me. I prefer usually to give talks on the blackboard, but
Oh, wait, yes, yes, yes. But yeah, I think we agree that Blackboard talks are nice, and in person, of course, conferences are nice. But our organization, it's for people from Latin America, and we cannot travel, unfortunately.
yeah.
So it's
No, it's a very good substitute.
yes.
Ah.
Yes, yes. So after COVID, I think this was a great substitute. Also, it opens this door for us to also bring this online and hybrid
Absolutely,
also.
yeah, yeah.
Yes.
Yeah.
Yeah. Yeah, I am located in Germany, and I am also super. It's super hot here. Sorry, I am like red with this air thing in my face, but it's not helping too much. Uh,
Yeah.
yeah.
I mean, it's also very useful.
Yes, yes, yes.
I mean, we should not complain because when you have this, this is a protection, I think.
Yes, yes, yes. Yeah, yeah. Because in my so in Germany, I don't
Mm.
Oh,
know everything. Keep warm, but yeah, for summer is not the best option.
Yeah. So I understand that you are in Germany right now.
Yes, I am in Germany right now. Yes,
Where in Germany?
in Kaiserslautern. It's called Kaiserslautern. It's in
Of
this.
course, I know that name. Yeah, yeah.
Yeah, when you go to Paris, we have a direct line to Paris.
Yeah, I know the name. Yeah, yeah. I think that Frank Schreier was there at some point. Yeah. Mm.
Ah, oh,
Maybe he is not anymore there.
yeah, okay. Yeah, I
but
don't.
but the weather was always in the same way, or is a special time for Europe this year?
No, it's very special. Yeah, yeah, yeah.
Okay, just before starting the talk of Professor Wasan, just a kind reminder that Professor Wasan, you will not see participants in the Zoom platform because all the participants are watching your presentation by YouTube, and from there they are going to make
Okay.
questions, and then Andrea will read the questions, and this is for security reasons of the platform.
Okay,
Okay?
okay.
Thank you very
So
much.
yes, I am not that surprising. It's not surprising if there are only 4 people
Yes,
attending.
right.
No.
And at this moment, we have close to 30 participants, and we expect the number to increase during your session. Okay?
Okay,
Thank
okay.
you very much.
Thank you for mentioning it. Yeah.
Okay. Okay.
You can tell me when can I start?
Okay. I will start the recording on Zoom also,
Okay.
and you can start.
Yes. Okay. Good morning and good afternoon, everyone. It is my great pleasure to introduce our next speaker, Professor Claire Voisin. Professor Voisin is professor of algebraic geometry at the Collège de France and is widely recognized as one of the world's leading mathematicians in algebraic geometry. Her groundbreaking work has profoundly influenced Hodge theory, algebraic cycles, complex algebraic geometry, and mirror symmetry. She is also the author of several influential books on Hodge theory that have become a standard reference in the field. Throughout her career, Professor Voisin has solved several major problems in algebraic geometry, including fundamental results on the Kodaira and Green conjectures. And she famously showed that the natural generalization of the Hodge conjecture to compact Kähler manifolds is false. Her contributions have been recognized with many of the highest international distinctions in mathematics, including the Shaw Prize and CNRS Gold Medal, the Clay Research Award, the Ruth Little Saturn Prize, the VA Frontiers of Knowledge Award, and most recently, 2024 Crawford Prize in Mathematics, becoming the first woman to receive this distinction. Today, Professor Voisin will present her lecture entitled Points and Zero Cycles of Algebraic Varieties. In this talk, she will discuss how the Shaw group of zero cocycles provide deep insight into the geometry of algebraic varieties, with applications to rationality questions and boundedness phenomena. Please join me in giving this a warm welcome to Professor Claire Voisin. Thank you very much, Professor.
Okay, so I thank the organizers for inviting me to give this talk, and thank you, Andrea, for this introduction. So usually, as it was mentioned, I work in complex algebraic geometry, and so in complex algebraic geometry, it's rather obvious what is the point on the complex variety. But this talk will be about algebraic geometry over non-algebraically closed fields. So I have to tell basically what is the point in that context. So it's little oriented towards arithmetic questions. So I am going to do algebraic variety over a field K. So let's the simplest definition of an algebraic variety is the case of an affine variety defined over that field K. So it's simply a closed algebraic subset which is contained in some affine space of dimension capital N, and it is defined by a finite number of polynomial equations with, but this is an important point, with K coefficients. And what we call a K point on such X, this is simply a common solution of this equation. So that means that you want an n-tuple of elements of K, x1 to xn, such that all the equations, the defining equation pi, vanish on that point. So it's rather obvious. And we use the notation x of K for the set of K points. And of course, now if you consider a larger field, an overfield L containing K, of course, one can see naturally the X as a variety defined over L. And we can search for the L point of X, namely that will be the solutions as above with coefficients in L, and then we will use the notation X of L. Now, the affine situation is simpler, but for me it will be very important to do projective algebraic geometry. So projective, it's the analog of for algebraic geometry of compactness in topology. So it's very important. And in projective geometry, the X will be contained in projective space in n dimension, and the defining equations will be, there will be homogeneous polynomials pi of x0 xn. Again, the pi have to be with with a K coefficient. Of course, when you start from an affine variety, there is a naturally projective completion, which the affine space sits inside the projective space, takes the Zariski closure, and the corresponding operations on the defining equation is simply that when you start with the equation pi of x1 to xn, you can homogeneize them by adding the variable x0 to make the polynomial homogeneous. So, and then, of course, you have the same notion of a point. Now, the important fact of working over non-algebraically closed fields is that, in some sense, many interesting algebraic varieties defined over a field K have no K points. So they have no points, which is a little troubling. Typically, if you consider the equation sigma of xi squared plus 1 equals 0, just one defining equation over the field of real numbers, you get no R point. But an important fact is that still, if your X is non-empty, you will always get points, maybe by replacing your field K by a finite extension of K. And the explanation for this statement, in fact, it's a sort of a version of the null-Stellensatz. You have your X, it is non-empty, it has a certain dimension, and you consider inside X a closed irreducible algebraic subset of dimension 0, defined over the same field. So it is simply a minimal closed algebraic subset of X. Minimal non-empty. And then when you look at the algebra of algebraic functions on this Z, in fact, it is a field which has to be a finite extension L of K. And then if you think a little, you'll get that this Z, in fact, provides a L point of X. So such a Z is called a closed point of X, and this is these mean the existence of the K points, the field extension needed to get L points will be in some sense the subject of this talk. I mean, how we can study this by geometric tools, knowing that I am not working in arithmetic, but in geometry. So to make sense of this story with this way of going back and forth between closed irreducible algebraic subset of dimension 0 and points defined over a finite extension, let me give the simplest example. You consider inside the affine space, the two-dimensional affine space, A2R, consider the conic defined by the equation x2 plus y2 equal -1. So this is the example that I used before. Then inside X, you consider the closed algebraic subset defined by y equals 0. So now there is no y in the equation. Your Z is now in the affine space A1R, and it is defined by the equation x2 equal -1. This x2 equal -1, when you extend to C, you get two solutions. That means that you get two complex points over C. So this is exactly the picture that we should have in mind in the rest of the talk. Okay, so let me speak about the degree of a zero cycle. So I consider an algebraic variety defined over a field K. I consider a closed irreducible algebraic subset of dimension 0 or closed point. I just mentioned before that is the same thing. And the degree of this Z is defined as the degree of the field extension. So I said that associated to Z, there is this so-called residue field, or definition field, if you like. L, and the degree of Z will be exactly the degree of that field extension. Exactly as before, we had this x2 equal -1, so this Z. I will say the degree of Z is 2 because this is the degree of the field extension from R to C. And so on. Now, zero cycle Z on X is will be by definition a formal combination with integral coefficients sigma of Ni of the Ni Zi, where the Zi are close point of X. And I use the notation Z0 of X for this group. This is a group in a stupid way, an abelian group, Z0 of X, which is of course enormous, which is of course much too big, but this is the starting, basically the object that we start with. And having such a zero cycle with Z, we define its degree to be the degree of Z equals sigma of Ni degree of Zi, and the Zi, I already defined what it is. The degree of Zi, it is the degree of the field extension needed to define the point, the close point Zi. Ok, so qu'est-ce qui se passe? So the group Z0 of X, so it's a point that I want to insist on. We are just apparently we are just looking at solutions of the equation. How to say? The group Z0 of X is very sensitive to the field K for various reasons. So first of all, if you have you start from your field K and you choose you make say for example finite extension. Then if you have an irreducible zero-dimensional Z containing X, so it gives you only one point, one close point over K. But when you change the field to L, for example, which is the definition field of Z, your Z is not anymore irreducible over L. So a close point, relative to K, when you change your field, it may give a bunch of close points, because it may give rise to several points, like I had this degree 2 close point in this conic, and over C, in fact, it gave me two complex points which are conjugate under the Galois group of C over L. And now yes, now another aspect is that so there is this phenomenon that one close point over K, when you change the field by finite extension, that can give you a bunch of points exchanged by Galois. But also when you take some transcendental extensions, typically when you use the function field of X to make a base for L, your function field of X, we will get the so-called generic point. This is a point that you cannot see by looking at close point or using only finite extensions of K. Okay, so this is in this sense that this group of zero cycles is very sensitive to the field. Last definition that I will need is that of the index. The index of X, so X is over K, and the index of X will be the positive, is defined as a positive generator of the image of the degree map. The degree map is obviously a group, an abelian group morphism, so from Z0 of X to Z. So the image, it is a set of multiples of a certain integer, and this integer is defined as the index of X. And if you look at the definition, this integer, it is a very interesting arithmetic notion, because it's also the GCD of all the degrees of the field, finite field extension needed to get point. Okay, so okay. And now So that was this group Z0 of X, but obviously it is much too large. Put all the points, I mean, it does not say at the end very much. So the essential object I am going to consider is rather the CH0 of X, the group, the Chow group of zero cycles on X, which is defined as the quotient of the group Z0 of X by rational equivalence, that is the quotient by the subgroup of zero cycles rationally equivalent to zero. And this subgroup, the definition is given here. It is generated as follows. So for consider all the curves contained in X or mapping to X. And then for each of the curves defined over K. And for each such curve, you consider a rational function. So maybe I have to ask that the curve is irreducible. And I consider a non-zero rational function on such curve. And a non-zero rational function on a curve, it has a so-called divisor. The divisor, it's a zero cycle on the curve, which is defined as the locus of zeros counted with multiplicities. That's why that gives a zero cycle, minus the locus of poles counted with multiplicities. So that is the divisor of a rational function. And so we consider this quotient, CH0 of X, and this is the interest of looking at the projective case. It's a very general fact that if X is projective, the degree of any zero cycle which is rationally equivalent to zero is zero. So of course that we reduce to the case. This is saying that on a projective curve, the divisor of a rational function has degree zero. And it follows that the degree map, which was defined before on the group Z0 of X, factors through the group CH0 of X. So this is very important because the group CH0 of X is much more, I mean, it's very hard, but sometimes it is really computable, while Z0 of X, it's, I mean, you cannot really compute it unless you can solve, I mean, unless you can describe all the parts. So, so let me give a very important example. I consider that will be the case of hypersurfaces of degree D in Pn+1. Let's consider maybe a smooth hypersurface. It's not very important for the moment. Such a hypersurface has naturally a zero cycle of degree D, which is well defined up to rational equivalence, and which is obtained as follows. So you have your X inside Pn+1, and in Pn+1 you also have all the projective lines. So P1, so it is defined by linear equations. P1 contained in Pn+1. And such a line, maybe if it is not contained in X, which is most often the case, it will intersect your X in exactly a zero cycle of degree D. The intersection will provide a zero cycle of degree D. And so that is saying that we have a canonical zero cycle of degree D on a hypersurface, which is obtained by taking the class of these intersections. And now there is a very nice lemma showing that in some case we can actually compute the index and even the CH0 group of hypersurface. I fix this is the following lemma. I fix the degree and the dimension. The lemma is that for the generic hypersurface xgen of degree D in Pn+1 case, the field K has been fixed. The generic hypersurface has a CH0, a cyclic group generated by this canonical zero cycle. And this canonical zero cycle, as I mentioned, it has degree D. So in that case, the CH0 group is very small, it is the Z, and the index, it is a non-trivial information, the index is D because the generator, it is a zero cycle of degree D. In this statement, I have to explain what I call the generic hypersurface, because it's really, in my mind, it's a very beautiful object. To define a hypersurface of degree D in say Pn plus 1 K, you need that, of course, you give you a homogeneous polynomial equation of degree D a priori with a coefficient in K. So your F will be given by a sum over all multi-indices I of total degree. So I is I0 to in plus 1, and you want that the sum of the index ig in a monomial is always a D. So this is what we call a homogeneous polynomial. So this F defines a hypersurface of degree D in Pn plus 1 K. And so the trick is to consider the field. So it's a purely transcendental extension of K, which is generated by the alpha I. You see the alpha I as indeterminate, not as element in K. And so you have this big field K prime, which is freely generated. This is a purely transcendental extension of K, generated by alpha 0 to, by the indeterminate alpha 0 to the, by the indeterminate alpha I for all multi-indices of degree D. And by a sort of by a sort of how to say, tautology, or there is a canonical equation which I denote by Fgen, to say that this is a generic equation, which is simply sigma over I of alpha I xi. Now the trick is that before my equation was in coefficients in K. And now I take my alpha I to be indeterminate in this field K prime. And this is what we will call the generic hypersurface in Pn plus 1. Now it is in Pn plus 1 K prime. So this is what we call the generic hypersurface. And this hypersurface, it is defined over this big field K prime. So it's very important because it's a way of looking at all the hypersurfaces at the same time. See, because instead of fixing the coefficients alpha I take them, how to say, as indeterminate, saying that if I want to consider a specific hypersurface, I will specialize my indeterminates to take this and this value. So this is really, for me, a very important object. But also the key point is that this object, it is a hypersurface defined over a non-algebraically closed field, highly non-algebraically closed. And even when K equals C, this generic hypersurface, it is, as we will see if I arrive there, it is a very interesting object as a variety defined over a non-algebraically closed field. So now let me come back to the generalities about the CH0 group. I come back to a very classical fact about the CH0. This is a case where the variety X is a smooth projective curve, say, of genus G over K. Maybe the genus makes more sense if the curve is irreducible or even geometrically irreducible. Let's ignore this. So in any case, I don't need the genus for the moment. So it's a general fact that for a smooth curve, the group CH0 of X is isomorphic to the group, the so-called Picard group, Pic X, of line bundles on X. So I should say rather isomorphism classes of line bundles on X, where the group structure is given by a tensor product. And to see why, how this such statement can be true, the fact is that if you have a closed algebraic subset of dimension 0 in X, there exists, call it Z, there exists a line bundle LZ on X with an algebraic section SZ, which has exactly Z as a vanishing locus. And now, if you consider now say Z and Z prime, and suppose that the two corresponding line bundle LZ and LZ prime are isomorphic, which is the case if well, these line bundles that define elements of the Picard group, and I assume that the two line bundles are the same in the Picard group, isomorphic, so the same in the Picard group. So if you have this isomorphism, then you get two sections of the same line bundle, and then the quotient of these two sections, SZ over SZ prime, this is in fact a rational function of X, and the divisor of this rational function is exactly the difference of the two divisors of SZ and SZ prime, so this is exactly Z minus Z prime. And so you conclude that Z is rationally equivalent to Z prime. So this is the way that we construct, the way that we prove this theorem. And now, now comes the notion that will be important for this talk. This is the following fact. Suppose that my smooth projective curve is also irreducible, maybe geometrically irreducible if you prefer, of genus G over K. Then any zero cycle Z in CH0 of X, which has degree at least G, is effective. And the meaning of effective here is that Z is rationally equivalent to a cycle sigma of Ni Zi, so here the Zi are closed points, where all the coefficients Ni are non-zero. I could consider only a strictly positive if my Z is different from 0. And for the proof, I have my Z. By the previous theorem, there is a line bundle, corresponding line bundle LZ, together with a rational section, sigma Z, with divisor Z. Now the section is a priori not an algebraic anymore because my Z, it is maybe not, it is a difference of two things. So I just have a rational function, sigma Z, with divisor Z. Now the point is that the line bundle LZ has degree equal to the degree of Z, and this and so by assumption this degree is at least G. And then you can apply the Riemann-Roch formula to this line bundle, and the Riemann-Roch formula will this is a so-called Riemann-Roch inequality. It will give you that the H0 of XL is different from 0, meaning that there exists a non-zero section of the line bundle L on X. And so there is this non-zero section sigma prime, and its divisor Z prime now, it is an effective zero cycle because sigma prime is algebraic, it has no poles. And this Z prime, by the previous theorem, it is rationally equivalent to Z. And so this is the proof of this corollary. And so this is saying that for well, maybe algebraically close if you like, that's not very important. This is saying that the group, well, maybe let's assume that K is algebraically closed. Well, we see that the group CH0 of X of 0 cycles of degree 0, I put a 0 here, CH0 of X 0. It is an irreducible algebraic group of dimension G, which is birational to the symmetric product X to the G, just because we pass from we add a fixed Z of degree G, So we can pass from zero cycle to degree G cycles, and the degree G cycles, they have been described in the corollary as being effective up to rational equivalence. And then, well, there is behind the so-called Abel theorem that gives you that it is birational to extreme. And so that means that the group CH0 of X0 is representable in the sense that it is parameterized by an algebraic variety. And what we are going to see is that this statement about the CH0 group of an algebraic curve tend to become completely wrong for higher dimensional varieties. Okay, so now I will discuss the case of higher dimensional varieties, and I'll start with surfaces, and I will explain my original motivation to study this question. So this is a beautiful conjecture of Castles and Swinnerton-Dyer, which concerns cubic hypersurfaces, smooth cubic hypersurfaces, X in Pn plus 1, defined over a field K, maybe of characteristic 0. I am not completely sure if it is important. And the conjecture says the following: if I of x equal 1, and I of x equal 1, this is the assumption that x has a zero cycle of degree 1. Then x has a k point. Of course, if x has a k point, the k point, it gives you a zero cycle of degree 1. Now, so this is the sort of converse for cubic hypersurfaces. So if we look at this conjecture, we see that we can first do the case where n equal 1, because it is exactly what we have done in the previous slide. For n equal 1, a smooth cubic curve, it is in fact a geometrically irreducible curve of genus 1. And so by what I have explained in the previous slide, a zero cycle of degree 1 on such a curve is effective. And now when you have an effective zero cycle of degree 1, that gives you a k point, because you write it as a sigma of ni xi, where the ni are all positive or non-negative. And you have the condition that sigma of ni degree of xi is equal to 1. The only possibility is that there is only one ni which is not 0. It has to be equal to 1, and the degree of xi is 1. So a zero cycle, an effective zero cycle of degree 1, then gives you a k point. So okay, and now already starting from n equal 2, this conjecture is still open, and maybe it could be in fact could be wrong. But there is this intriguing result established by Corey in 1976, saying the following: so consider a smooth cubic surface of index 1. So exactly this is the situation of the Castles and Swinnerton-Dyer conjecture. So what Corey tells is that this cubic surface has a closed point of degree 1, 4, or 10. So it's very so let me maybe make a little more precise. I mean, explain how to say the motivation for the statement. Our assumption is that the index of S is 1. Now the index, I recall, this is the GCD of the degrees of closed points on X. But the point is that X is a cubic surface, and a cubic hypersurface in general always has zero cycles of degree 3, which are obtained by, this is what I explained, this is by intersecting your hypersurface with a line, which is not contained in the hypersurface. that will give you 0 cycles of degree 3, which can correspond to a close point of degree 3, or maybe the sum of the various close point of degree, maybe 1 or 2, etc. So there are several possibilities. So in any case, our assumption, in fact, it is equivalent to the fact that our cubic surface S has close points of degree co-prime to 3. And what says Corey is that, in fact, it has close points of one of these 3 possible degrees which are co-prime to 3, 1, 4, or 10. One is would solve, of course, this Castle and Swinnerton-Dyer conjecture, but 4 and 10, what to do with that? So more recently, I improved this theorem by Corey by proving that under the same assumptions, S has a close point of degree either 1 or 4. That means in the Corey theorem, I remove the 10 and I say we can compute the index by searching only the point of degree 1, close point of degree 1 or 4. Okay, and then we don't know more about the Castle and Swinnerton-Dyer conjecture for cubic surfaces, and I am not sure if it is true, in fact. Let me say something about other similar varieties. So there are the so-called Del Pezzo surfaces. By definition, they are Fano smooth projective varieties of dimension 2. And it is known that there are finitely many families of such surfaces. They are indexed by their degree. Well, they have canonical, anti-canonical embedding, if you like. And so this degree ds, it can take only these 9 values. And to say a little more about Del Pezzo surfaces, at least maybe at least in characteristic 0 over over an algebraically closed field, they are all rational, so birational to P2, and more precisely, they can be obtained by blowing up the projective plane P2 at finitely many points, and these finitely many points, you can take at most 8 of them, so that's why finally you have bounded these bounds on the degree. And not only you cannot blow up any of these points, there is a generality assumption on the position of these points in the plane. So this is what is a Del Pezzo surface. But these Del Pezzo surfaces, they are also very interesting over non-algebraically closed field. And the degree 2 case, it is the case, this degree 2 Del Pezzo surface, the projective model is by considering a double cover of a projective plane ramified along a quartic curve. So, and Couliot-Hellène proved a result which is very similar to that of Corey. So this degree 2 Del Pezzo surfaces, they have canonical degree 2 zero cycle. So if such a surface has index 1, that means that it has close points of odd degree. And then Couliot-Hellène says if it has a close point of odd degree, then it has close points of degree either 1, 3, or 7. And another statement, interesting statement by Couliot-Hellène is the following bound. So I mean, it's a sort of generalization of Corey bounds, and this one in the case of degree 2. There exists an integer n which depends on nothing, such that any Del Pezzo surface of index 1 over a field of characteristic 0 has close points of degree bounded by n and globally coprime. So you see the assumption that the index is 1, it is saying that there are close points of globally coprime degrees. But what Couliot-Hellène says is that there's a close point, you can choose them of a priori bounded degree, a priori bounded by this number n that depends on nothing. Okay, so let me go toward another notion of boundedness for del pezzo surfaces that is closer to what we have seen in the case of zero cycles on a projective curve. So I prove that there exists an integer n that depends on nothing, such that for any del pezzo surface S over a field of characteristic 0, any zero cycle of degree at least n is effective. So, that is already mentioned, rationally equivalent to an effective zero cycle. So it is a situation which is similar to what we have seen for zero cycles on projective curves, where we could take for n, for the integer n, the genus of the curve. And in fact, this statement about zero cycles being effective, it gives another proof of Colliot-Helen bounds, namely that we can compute the index using point of a priori bounded degree. And I should mention that this theorem had been established by Colliot-Helen before, assuming that the surface has a key point, which of course is a rather important assumption. And now the notion of boundedness that I want to describe and to study is, well, it's just put in a definition, something that we have, a phenomenon that we have seen twice in the case of curves and in the case of del pezzo surfaces. I will say that a projective variety X over a field K has bounded CH0 if there exists an integer n such that for any overfield L of K, this any overfield, I mean, I say actually any, not, I absolutely don't consider only the finite extensions. And in fact, the result will be, the notion will be important also in the case where the field K is algebraically closed. So such that for any overfield L of K, any zero cycle of degree at least n on XL is effective. That means that I consider not only my X over K, but all the XL over L, all the I mean, for all field extensions, I mean, arbitrary field extensions are L of K, and I study the data of all the CH0 of XL. And this is important to do this because if you consider just the CH0 of X, as I explained, there was the example of the generic hypersurface of the degree D. I explained that the CH0 group, it can be very small. You see nothing. It's just Z generated by the canonical class. While of course, if you consider all the field extensions, you get all the points over all extensions. So in fact, you have plenty of information. So this is called the CH0 group, the universal CH0 group, considering all this data, and it's very important. So the example of varieties with bounded CH0s are the projective curves, and this theorem above, it tells you that del pezzo surfaces over a field of characteristic 0 have a bounded CH0. I would like to compare the notion of bounded CH0 and finite dimensional CH0 for the notion that was developed by Mumford in a very important work going back to 1968. Mumford works with a smooth projective variety over C, and he makes the following definition. He says that it has a finite dimensional CH0 group if there exists an integer n such that any zero cycle on X of degree at least n is effective. So you may wonder what is the difference between Mumford definition and the notion of boundedness. It's simply that you see here I am not considering only the CH0 of X, but all CH0 of XL for all field extension L of C. So the difference between the two notions is that X, Mumford only looks at the CH0 of X for my X over C. And in fact, I will consider all CH0 of XL for all field extension, which could be as well transcendental, purely, for example, the transcendental extension of C. And there is much more information in them. And Mumford established a very result that has been extremely important for the later on for the theory of motifs and for the relationship between the study of Chow groups of a variety over C and Hodge structures or geometry, topology. He proves the following. Let X be smooth projective over C and assume that CH0 of X is Z. That is, CH0 of X is Z. That means exactly that all points are rationally equivalent. Then X has no non-zero algebraic forms of positive degree. And similarly, I mean, maybe more subtle theorem, assume that X has finite dimensional CH0 in that sense, in the sense of the definition above. Then the algebraic forms on X of degree at least 2 vanish. Of course, you can have a non-zero algebraic forms of degree 1 as shown by the example of algebraic curves. Algebraic curves, they have bounded CH0, but they have algebraic 1 forms. So there is this remarkable distinction, trivial and bounded, and this is related to the behavior of algebraic forms. Just a remark for those who know better the story over C. If we are over C, we can also consider X as a complex manifold just by saying I see X inside, I consider the space of C points, so this is inside projective space, some complex projective space. And complex projective space is a complex manifold. The algebraic equation defining X, local algebraic equation, I can see them as local holomorphic functions. So my X, it provides as well a complex, the set of complex points of X provides as well a complex manifold of projective space. And then the Gaga theorem of Jean-Pierre Serre tells us that algebraic forms on X, they are the same as holomorphic forms on the corresponding complex manifold. So this gives some extra depth and importance to this theorem by Mumford, because then you can think to the Mumford theorem as something relating Chow groups and topology of the corresponding complex manifold, which I find absolutely remarkable. But still, I continue with my story over non-algebraically closed fields. So now I am going to consider Fano and more generally rationally connected varieties in higher dimensions, so the del Pezzo surfaces were Fano surfaces. So rationally connected, so consider a smooth variety over smooth projective variety over a field of character K of characteristic 0. I say that it is rationally connected, so I should say geometrically rationally connected. If over the algebraic closure K bar, there exists a dominant rational map from variety of the form Y cross P1 to X, such that this map, when you restrict it to, so in P1 you have 0 and the point at infinity, you restrict this variety, this rational map to Y cross 0, you get something that is dominant. That is, you catch any point over K bar, for example. And when you restrict to Y cross infinity, the map that you get is constant. So it's, I mean, topologically, sometimes it's very nice, and it looks like you have a sort of homotopy between the constant map and the map that is surjective on points or something like that. And in particular, The Fano varieties X, those are the smooth varieties with minus the canonical bundle ample. So typically, if you consider hypersurfaces of degree D in Pn plus 1, where D is none greater than n plus 1, they are Fano. There is a very important theorem due to Kolar Miyaoka-Mori, also separately to Campana, proved in 1992, that tells that Fano varieties in characteristic 0 are rationally connected. So, and now what they do, these varieties in my talk, is the following lemma. If X is rationally connected over an algebraically closed field of characteristic 0, then CH0 of X is Z, in the sense that all points, in fact, over an algebraically closed field, CH0 of X is equal to Z. This is exactly saying that all points, all K-bar points are rationally equivalent. And the proof is simply that through using this map, dominant map phi, you see that if through any point x, I said x, I wrote x here, I should say x of k-bar, to any k-bar point x, there exists a rational curve phi of y cross p1 for some y, because this map is dominant, which passes through x, and also through x0, because you consider the map phi restricted to small y times p1. That will give my rational curve. And so that says that the existence of this map from p1 to x, passing to x and x0, shows that they are rationally equivalent. And that's finish the proof. And now what we are going to do, that will illustrate, if you take for K the field C of complex numbers, we are going to exhibit examples of varieties that are rationally connected. So by this lemma, they have a trivial CH0, but then that have unbounded CH0. That illustrates the difference between the CH0 of X and this universal CH0, where we are considering all the CH0 of XL for all the field extensions C contained in L. So let me explain why this slide is supposed to explain the importance of considering these field extensions of C, and how you can get interesting points by going to this field extension. So starting from any x over k, I will prefer the characteristic k equals 0, also maybe k equal k bar, but it's not very important. The fields that we are going to consider are as follows. First of all, there is the generic point. For this, the field that we are going to consider is the field L1, which is simply the function field of x. This is k of x. Now, I say that there is an interesting point of x over this field L1, which is simply the generic point. So how is it defined? So the extended variety xL1, so when you consider x over the field k of x, is just you can see it as the generic fiber of the first projection from x cross x to x. Generic fiber, that is, you just consider this projection over arbitrarily small Zariski open set of x. Now, inside x cross x, you have the diagonal. The diagonal, it is the section of the first projection from x cross x to x. But over the generic point of x, this section, it gives you exactly a point which are denoted by delta x, which is a L1 point of of X majority X L1. So and this generic point, it is very important if now you can of course suppose that you have a point x defined over k. You can consider the difference delta x minus this constant point extended to the field L1 that provides a zero cycle of degree 0 on x L1. And if you know that this zero cycle is of degree is rationally equivalent to 0, then the variety has a universally trivial CH0, and in fact that tells you that all CH0 of XL0 are 0 for any field extension. So what I am saying is that just by looking at a single extension L1 given by the generic point which is defined over K of X, you can check whether your variety has universally trivial CH0 or not. And for unboundedness, we are going to study infinitely many points over the different fields that are defined as follows. So the point will be what I call the generic degree K point. Here it is a generic degree 1 point, if you like. So I do the following. I consider the case symmetric product. So this is maybe I prefer to work with smooth variety. So I remove the diagonal. So I consider x to the k minus its diagonals, and I quotient by the symmetric group. So that gives me a smooth variety, which is a case symmetric product. And this smooth variety. So that inside it carries the universal correspondence, and it's a closed algebraic subset gamma k in x0k cross x. So it's just the set of z in the symmetric product x, where x belongs to z. So it has clearly degree k over x0 to the k. So this is really a topological construction, in fact. And now the LK will be the function field of this x0 to the k, and the generic fiber of gamma k over LK over x0 to the k will give me a degree k point delta xk of xlk. So this is what I call the generic degree k point. So and here are the results obtained by studying this degree k, all these degree k generic points. I prove the following. If n is at least 3 and d is at least 2 times n plus 2 over 3, so let's say that d is even for simplicity. The very general hypersurface X, the complex hypersurface X of degree d in Pn plus 1 has unbounded CH0. And when I say the very general, that means I am over C. I have a certain parameter space for all complex hypersurfaces of degree d. And inside this parameter space, I can choose one. So there is a countable union of closed proper algebraic subset. Such that if I choose my equation in the complement of this countable union, then it will satisfy this statement. So this is the proof is obtained by studying the rational equivalence class of this degree n. I mean, there's a degree n plus dk generic point minus k times the canonical cycles, and I prove they are not effective. So for n arbitrarily large, and so I get the result. And another statement, I finish with this. I come back to this rather Core tape, I mean, it's a different question, more algebraic, less geometric, more arithmetic, and less geometric. This is showing that no Core bound can exist for higher dimensional Fano threefold. So the result is that there exists a quartic threefold over a field K in characteristic 0, such that for any odd integer n, there exists a field Ln containing K, such that the quartic threefold seen over Ln has a point of degree n, but no close point of odd degree smaller than n. So this is a situation exactly, so this quartic threefold, they have index 1 because they have 0 cycles of degree 4 obtained by intersecting a line with x, but they have a 0 cycle of degree 4 and a point of odd degree, so they have index 1. But to compute their index, we have to look at points of odd degree, and there was no bound for the degree of for the odd degree of points. Okay, so I should stop, and I'm sorry, I was supposed to stop 5 minutes before, and I completely forgot. I'm sorry about that.
Yes, Professor. Thank you very much for your nice and interesting talk. Now we will be open for questions. In YouTube, you can just write your question. Okay, I have one question. Yes, you mentioned in the beginning for some step of one proof that you use Riemann-Roch theorem.
Sure, yes.
So you have, so instead of these divisors, you consider this line bundle on set, right? Yes.
Yeah.
Yes. So this Riemann-Roch here, it's this H0 minus H1 equals to 1 minus the genus plus, okay.
Yeah.
Okay, and this gives you this existence of non-zero global section
because what H0 of XL is the dimension of the space of sections.
Okay.
So you're right, the Riemann-Roch formula, it is an equality.
Yes.
H0 of XL minus H1 of XL equal degree of L plus 1 minus G.
Yes.
And so it tells you that if degree of L is at least G, H0 minus H1 will be at least 1, but the minus H1 that says that H0 is greater than or equal to 1. So that, and this H0, it is a dimension. This is the dimension of the algebraic sections.
Okay. So this gives you this effective divisor.
Absolutely.
Yeah, okay, I see. Okay, thank you. Maybe I can ask you one last question. Is somehow related, or can we relate these CH zeros? Because I saw this Riemann-Roch formula, so for sure you have some index theory parallel to L somehow.
Yeah.
Can this be studied for index theory, or this question may not have any sense?
I know, but it's a very important question. In fact, you see, for the case of curves, we have this remarkable correspondence between line bundles and zero cycles.
Yeah, okay.
And in fact, this correspondence, it is somehow of a topological nature. It is really saying these things if you are a differential geometer, you associate to, it's more general to hypersurface a line bundle. A line bundle, it's a vector bundle of rank 1 with a section such that the zero set of this section is exactly the given hypersurface.
Yeah.
And in general, now if you have a zero cycles on a higher dimensional variety, what we would like to have is a vector bundle of rank equal to the dimension of the variety, with a section vanishing exactly along, for example, just have one point or finitely many points. You would like to have to define them as a zero set of a section of a vector bundle of rank equal to the dimension of the variety. But the problem is that this does not exist in general. So this correspondence between this is absolutely specific of code. In fact, the important point is this is specific of codimension one. This
Okay.
correspondence between hypersurfaces and rank one vector bundles. If you consider now higher codimensional subvarieties, you don't have a good correspondence between subvarieties of codimension R and rank R vector bundles. This is
Okay.
not completely true. In some cases, that works rather well. And in fact, for example, my work on zero cycles on del pezzo surfaces uses the possibility of constructing interesting rank 2 vector bundles associated with zero cycles, which are codimension 2 closed algebraic subsets. And so that means this correspondence still works rather well for codimension 2. And, and now for codimension higher than 2, it really breaks down in the sense that there are topological obstructions to that that are related to precisely two index formulas that involve that goes back to something that go back to Atian Hirtebroek. If you consider now subvarieties or closed algebraic or closed analytic subsets of codimension R with R at least 3, they are not in general associated to any rank R vector bundles, and in fact to any vector bundles. And this is a problem which is related to exactly to the fact that when you do Riemann-Roch tape formulas, you have denominators. These denominators, they are there, and they prevent usually to have this good correspondence.
Okay, thank you very much. We have one last question from YouTube. Alexandra Garcia asks if I wonder if some of the results you have shared are valid or could be extended for vector bundles or fiber bundles over del peso surfaces.
For projective for projective bundles, if it is actually a projective bundle that comes from a vector bundle, you take a vector bundle and you projectivize it, there is a formula computing the Chow groups of a projective bundle over a variety. And in fact, in that case, for a projective bundle, the sage zero group is the same for the projective bundle and for the base. But I think that already if you take, I have to check this. Maybe already if you consider non-trivial Brouwer-Severi varieties that are they are a sort of projective vibrations that are not coming from by projectivizing vector bundles, or if you like, there are vibrations that when you pass to the algebraic closure of the field that become projective bundles. And then, so this is a tricky thing that exists sometimes. And I think that in that case, you don't you don't necessarily have the same stage zero, and the results, I think, I have to, I mean, the stage zero may change in that case, and I have to think, I mean, it is not clear to me if boundedness is preserved. This is a very good question in any case. But it's not clear to me if that will work for broad varieties. But for projective bundles, yes. I mean, projective bundles coming from vector bundles, projectivized vector bundles.
Okay, Professor, thank you very much for coming today and being here with us today. We have 52 viewers from YouTube. Yeah, it's great. Again, thank you very much for your nice talk. And on behalf of the organizing committee, Professor Claire Bossan, thank you very much for being here. It has been a great honor and having you here, of course. So thank you very much for everything.
Thank you for the invitation. I'm happy to give this talk.
Thank you, Professor.
Bye.
Bye.
Okay, thank you very much, Andrea, for chairing the session of Professor Boissan. Thank you very much, Professor Boissan. It seems many people was very interested in your talk. Thank you.
Thank you very much.
Now,
It's very kind.
so now I would like to invite Professor Antonio Cordova. Professor Cordova, can you hear us?
Yes, I can.
We have a small delay maybe in the time, but thank you very much for waiting for us a little bit. How you would like to make your presentation? You are going to use the board?
We are going to share
Screens. Okay, very good. I think we can see your screen.
Yeah.
We can see your screen. The title, right, is the Hausdorff dimension of sets containing circles in many directions, right?
That's right.
Okay, very good. So please just let me make a short presentation about yourself.
Okay.
And we will be happy to have you 45 minutes, 50 minutes, plus 5, 10 minutes of questions. Up to you. Thank you very much for accepting our invitation.
Well, thank you for the invitation. I am very glad to participate in this meeting.
Okay. So then to our attendees of ICMAM Latin America, people that are following us in Latin America, in other parts of the world, it's really my great pleasure to introduce you, Professor Antonio Cordova. Professor Cordova began his undergraduate studies at the Complutense University of Madrid, and while still an undergraduate student, was admitted to the prestigious University of Chicago, supported by the eminent mathematicians Alberto Calderon and Anthony Sigmund. Professor Charles Pfefferman, later a Fields Medalist, and at that time the youngest professor in the history of the university, became his doctoral advisors. Both were, Professor Cordova, if I am not mistaken, 20 years old then, and this marked the beginning of a friendship and close collaboration that continues until today. The results of his doctoral thesis earned him an invitation to Princeton University. Moreover, the excellence of his work, including the resolution of a conjecture proposed by Sigmund and published in Annals of Mathematics, allowed him to remain at Princeton for 8 more years. His research has been remarkably diverse, ranging from number theory to harmonic analysis and partial differential equations, as well as mathematical physics. His scientific output is of extraordinary quality, with around 100 publications in leading international mathematics journals, has Annals of Mathematics, Inventions, Communications in Mathematical Physics, Duke Mathematical Journal, among others. His contributions to the Spanish mathematical community has been highly significant. He was a founder of the Revista Matemática Iberoamericana in 1982 and played a key role in the establishment of the Royal Hispanic Mathematical Society, where he served on his board of directors and was the first president of his scientific commission. On September 30 of 2011, He was awarded the National Research Prize Julio Rey Pastor in the area of mathematics and information and communication technologies. According to the official statement from the Ministry of Science and Innovation, the award recognizes his original, profound, and fundamental contribution across different fields of mathematics, particularly in Fourier analysis and partial differential equations. Professor Antonio Cordova, thank you very much for accepting our invitation. Please
Thank
go
you.
ahead.
I am glad to participate in the meeting. In the following, I will talk about a very recent result, in fact, an unpublished result, which is closely related with the well-known Kakeya set problem. Can you hear me?
We can hear you well, yes.
Okay. The problem is the following. Given a circle, a one-dimensional circle SR in R3 as the boundary of a planar disk dr, let us define the direction of the circle SR to be the normal direction to the disk dr. Okay? When we have that, we shall consider bounded set K, capital K, contained in three-dimensional space, R3, in such a way that inside K, we can place a disk, and this XR, on each spatial direction, theta. So we have inside K a disk placed on each spatial direction. And then the theorem that I will discuss in this talk is that under those hypotheses, the Hausdorff dimension of the set K has to be greater than or equal to 2. And observe that this estimate, this lower bound for the Hausdorff dimension, is best possible because the sphere S2 is an example that we cannot go beyond that. Now, let me remark that in the method of the proof that I will sketch, I will present briefly in my talk, yields the same result for other rectificable curves, for example, for ellipses and so on. But it leaves open the non-rectificable case, like, for example, the well-known snowflake, von Koch snowflake. Also, that there is an extension of the theorem to higher dimension. Higher dimension means n greater than or equal to 4. So suppose that we have a bounded set capital K contained in Rm, and the hypothesis is that this capital K contains a d-2 sphere on each spatial direction, that we can place such a d-2 sphere in Euclidean space Rn. Under that hypothesis, we also have that the Hausdorff dimension of this set K has to be greater than or equal to d-1. As before, this is shut. My last remark is that the case n equal 2 is peculiar, and if I have time, I will make a few comments about what happened when the dimension is 2. The theorem 1 will be a corollary of a more powerful result. Suppose that in R3, we fix a direction, let's say a north-south direction by that time, and then we consider all other directions perpendicular to that line. So just to precise, let's define a circle of direction E to be the equator, and we will consider object, I mean, a cycle with having those directions. As I recall, the direction of the circle is the direction perpendicular to its plane disk. And now the theorem is that under that hypothesis, if the set K is a bounded set which contains a circle SR theta, so the radius, it depends on the direction. It contain a circle SR theta on each direction of this equator, then also we have the dimension of the Hausdorff dimension of the set capital K has to be greater than or equal to 2. As I say, this is a reminiscent, is closely related with the well-known Kakeya set problem in n-dimensional space. Now, as usually happens when we have to compute the Hausdorff dimension of a set, we have to consider covering of the set capital K by dyadic cube of side length. Let's say the length of the cube Q sigma is less than fixed 2 to the minus K naught. K naught will be changing, and then we'll have to take the infimum of those estimates. So in this covering, the set K is contained in a union of Q sigma. This union is a stratified union, so we have a union over K greater than or equal to K naught of the union of all the cube in the covering of side length 2 to the minus K. So the union inside is all this cube has length 2 to the minus K, and then we take the union of all these families. And in the computation of the Hausdorff dimension, these covering are relevant. As I say, the cube, Q sigma K, belong to a mesh, a dyadic mesh in Rn of length 2 to the minus K. Let us define Ek to be the union of all the cubes in the covering of the same size, 2 to the minus K, and let us denote by Nk the cardinal of this, the number of cubes of such of that family of this mesh 2 to the minus K covering K. And then the proof of the theorem about the Hausdorff dimension will follow if for every alpha less than 2, remember we're going to prove that the dimension is 2, then for every alpha less than 2, there exists a positive number lambda alpha, so that this sum is greater than lambda alpha, which is greater than 0. So this is just applying the definition of Hausdorff dimension to this particular case. Now, in mathematics, often in mathematics, also in life, in ordinary life, to prove, to obtain some result, it's better to be ambitious and bet for a more powerful one. That will happen here. In fact, we will get this inequality proving something stronger. So we'll prove that for every alpha less than 2, there is a positive number lambda alpha, such that for every covering of this kind of the set capital K, we have the inequality that Nk 2 to the minus K alpha is greater than or equal to lambda alpha, which is of course bigger than 0. So this is the claim, and this claim will imply that the dimension, the Hausdorff dimension of the set capital K is has to be greater than or equal to 2. Now, to continue, let us, as I say, the radius of those circles are arbitrary. We have no constraint, no hypothesis about the radius. You may, particularly interesting case when all the radius are equal, say, to 1. But in the theorem, we have no such hypothesis. Nevertheless, let us observe that we can choose always a constant, a positive constant, such that the set of direction, so we parameterize the direction by point in the equator E, the set of direction such that the corresponding radius is between C and 2C is a set which have Hausdorff one-dimensional measure, I mean length, capital R greater than 0. So this is more or less obvious if we apply the definition. The measure of E is fixed, and of course for a family of different C, they cover E, and one of them has to be of positive measure. Then let us define to be E prime the subset of the equator, the subset of direction, so that the corresponding radius of the circle inside our set capital K is between C and 2C. And also, let me, given such a circle, this is the circle here, we have the direction north-south, and as is said in the theorem, the direction of the circle is theta is perpendicular to this line, so we can parameterize by a point in the equator. So we have this circle, and then given the situation, the north, the south, the equator, this circle can be divided into, let's say, 8 octons. So 8 octons of equal length. Among these 8 octons, so let us choose one of them, which is not does not contain, does not pass through the north or south pole. So it's somehow touching the equator. Let's say this one. Doesn't matter if you take this or this over here. For each one of those circles SR theta, we choose one octant not passing by the pole, and let's call that octant SR theta 1. And then the lemma, the crucial lemma is that for each beta greater than 0, given we can find a positive lambda beta and a k greater than or equal to k naught. Remember, we start with a covering in which k naught was give us the biggest side of the cube. So for each beta bigger than 0, we can find a positive lambda beta a k such that the length of this octant intersection with the set Ek. Remember, the set Ek is the union of all the cubes in the covering of length, side length 2 to the minus k. So the one-dimensional Hausdorff measure of this intersection is greater than or equal to this constant lambda beta by 2 to the minus k beta. Okay, and this inequality happen for all direction theta in this subset of direction E prime that we have determined before. Now this lemma is very easy, because if we look at the Hausdorff, I mean, how many? What is the Hausdorff one-dimensional length of this octant? Is the length of the circle divided by 8. So it's 2 pi r theta divided by 8, pi r theta divided by 4, and r theta is greater than this constant c. So we have an estimate by below of this length. But on the other hand, the circle is contained in the set capital K, and therefore this octant is contained in K, which is contained in the union of the cube of the covering. And so this length is less than or equal to the sum of the length of this octant in the set EK for different Ks greater than or equal to K naught. Now, this is obvious. And now let's that's what we want to prove. We want to prove this inequality that there is such a K. So suppose that this inequality is false for every K. If this inequality is false for every K, so we have the opposite inequality, then in this identity here, we will have that this is less than lambda beta 2 to the minus k beta for every K greater than K naught. And if we introduce this in this equality, we'll get that this number. Sorry?
No, Professor, I think that just one of the organizers stopped the recording, but please continue with your presentation. Sorry.
Okay, so we will get this inequality that pi c over 4 is less than lambda beta, the sum of this geometric series, which can be has this sum, and now this inequality is obviously false for lambda beta small enough. So it cannot be true. Therefore, there is a beta for which this inequality has to hold. And that's the lemma. So there is an EK, K greater than K naught, so that the portion, the one-dimensional length of my octant inside this set EK is big enough. And big enough is lambda beta multiplied by 2 to the minus K beta. And having established that, let us define the set omega K to be the set of direction in this subset of the equator, the subset of direction where this inequality holds. By the lemma before, we know that the whole E prime, the whole set E prime, must be contained in the union of omega Ks, because for every theta in E prime, there is a K where this inequality holds. So therefore, E prime is contained in this union. And from here, we get that the H1 Hausdorff measure, the length of this set E prime is less than or equal the sum of the length of this omega Ks. And therefore, by the same argument as before, we can find a K greater than or equal to K naught, so that the length of this set omega K, H1 length of omega K, is greater than lambda beta 2 to the minus K beta, because otherwise we will have the same contradiction as we discovered in the lemma. So there is a K greater than of K naught, so that the length of this set omega K in the equator is big enough. It's lambda beta by 2 to the minus K beta. And now, if we have a set in the equator of direction, which has this size, this estimate for each side, then we can select a number of points between the direction in omega K, which are 2 minus K far apart. This is just an elementary circuit. We could have this number of points far apart, then the length of omega K could not be greater than lambda beta 2 to the minus K beta. So we can select all these points of the direction in omega K. Let's call this direction theta j. And if we order this theta j in appropriately, linearly, then those points, those directions, will satisfy this inequality the distance between two of them will be greater than or equal to 2 to the minus k multiplied by j minus 1. So we have a certain amount of direction which are well spaced, and for each one of those directions we have control of the overlapping of the corresponding octane with the set ek that we want to control. Okay, so now having established that, let us define d theta j to be the set of points in R3 whose distance to the octane, corresponding to the direction Rj, is less than 2 to the minus k. In the terminology of Mandelbrot, which, as you know, is one of the creators of the fractal notion of the Mandelbrot called this object the Minkowski sausage of the octane SR theta j. So the point which are at distance less than 2 to the minus k. So you can imagine it's just an octane is just an arc, and then we have a sausage of point which are at distance 2 to the minus k of this arc. Similarly, let us denote by d theta j tilde to be the Minkowski sausage, now not of the whole octane, but of the octane intersection with ek. Okay, and the point is that these two objects has the volume. This is the area, the three-dimensional volume of this intersection is comparable to the volume of delta j tilde. This is just elementary geometry, and then if we want to estimate this volume, remember that this volume is Minkowski sausage are points which are at distance 2 to the minus k of a object, a linear object, which has length greater than lambda beta 2 to the minus k beta. So to each point in this, this is a subset of the octane. At this point, we add a circle in the perpendicular direction of radius 2 to the minus k, and by Fubini or whatever, or Cavalieri, we have the estimate of the volume of such Minkowski sausage is given by the product of this length by the circle that we are in the perpendicular direction. So we have this estimate, and then on the other hand, we know that the cardinal, the number of directions that we have in this set omega k is given by this number. Is lambda beta 2 to the k 1 minus beta is the estimate we obtained before. And putting together these two estimates that allow us to compute this, to give an estimate for the sum of the volume of in J and the number of those selected direction of the intersection of the Minkowski sausage delta theta j with the set ek. Remember, set ek is the union of the cube in the covering of psi length 2 to the minus k. And this sum has to be bigger than or equal to the product of them, because each one of them is estimated by this, and the number of them is this. So we get lambda beta squared, 2 to the minus 2k, 2 to the k, 2 to the minus k, and 2 to the minus 2k beta. So this is the estimate for the sum of this volume that we have here. Now, that estimate can be written down in this other form, intelligent form. So this is the lower bound that we obtained before, and remember, and this integral is just the sum of the volume, because this is the indicator or characteristic function of this set, the intersection, and so this integral is simply the sum of this volume. So this is exactly the inequality we had before. But now, writing in this form, we can apply Herder inequality because the set where we are integrating is the set, and we are integrating this sum. So by Herder inequality, we get a set to the 1/2, and here we have the L2 norm of this sum of indicator functions. But the L2 norm of the sum of this indicator function, when we decode what it means the intersection, the volume of the intersection, the sum in ij of the volume of the intersection of this set, which is less than or equal the volume of the intersection of the d theta j, d theta i. We eliminate k, we have an inequality to the right side. And therefore, at the end of the day, we have that this number is less than or equal to, this is less than the volume of Vk to the 1/2, and when we have to evaluate this intersection. But this intersection is the intersection of two of those Minkowski sausages. Remember, the width is 2 to the minus k, and the length is c, is let's say 1. And so, and the angle, the dihedral angle between the plane of these two octants is exactly I minus j multiplied by 2 to the minus k. So to evaluate this intersection is just an easy trigonometrical problem. Believe me, if we do the evaluation by simply trigonometry, we'll get that these volumes and this sum is controlled by a sum like this. So it's 2 to the minus 2k divided by I minus j plus 1. And I minus j give us the angle between the two planes. And finally, to finish, we just observe that we have the arithmetical inequality that this double sum is less than or equal to t log t, where t is the number of elements in this sum. But t is 2 to the k 1 minus beta lambda beta, as we were able to show before. So therefore, when we at the end of the day, we have an estimate for the ek. What do we have? The estimate for ek is we have to square this guy and divide it by the square of this, by this sum. And when we do that, we get for the measure for the volume of ek, we remember the volume of ek is the number of cubes in the covering multiplied by the volume of one of the cube, 2 to the minus 3k. And so this number, so this is greater than or equal to this, and this is the estimate we have obtained before by after doing the division that suggested the inequality about the volume that we obtained. And so now from here, we get that if we multiply nk by 2 to the minus k alpha, this is greater than or equal to lambda beta to the third power divided by k, and multiplied by 2 to the k 2 minus alpha minus 3 beta. And now remember that beta, it was any positive number at disposal. And therefore, if alpha is less than 2, we can choose beta positive small enough so that this whole thing is greater than lambda alpha greater than 0, and we have. So this is the sketch. I mean, I would say a detailed presentation of the sketch of this thing. Now, as I said, there is an extension for higher dimension n greater than or equal to 4, which I won't comment here, but the basic idea of the proof are already contained in the 3-dimensional case. The case which is peculiar, which is somehow different, is the case n equal 2 in 2 dimensions. So let me just discuss briefly what I know about the two-dimensional case. Let's define Z naught to be a Cantor set of points in the interval 0, 1, and these points are such that the expansion of X on base 4 contains only the digits 0 and 3. So geometrically, that means that we divide the interval 0, 1 into 4 equal pieces, 0, 1/4, 1/4, 1/2, and so on. And we eliminate the two in between and keep only the strings, 0, 1/4, 3/4, 1, 1. And then we repeat the same process with these two remaining interval, and so on. And when we do that, we continue this process infinitely many times. What is left is the Cantor set Z0 of point in the interval 0, 1, whose expansion in base 4 only contain the digits 0 and 3. And now let's, when we have Z naught, let's define Z naught tilde to be 1/2 of Z naught. So just a set of points, 1/2 X, when X belongs to Z naught. And now with these two sets, we place copies of them, copies of Z0 and Z naught at parallel horizontal line, I mean the line Y equals 0 and Y equal 1 in the plane. So let's C of XY is the set of points where X is in Z naught and Y is 0, and C tilde is the set of points XY where X belongs to Z naught tilde and Y equal 1. And when we have done that, then we consider the union of all the straight segment, the straight line segment, joining a point of the top C tilde with another point at the bottom C. So here is the picture we have in this interval. We have placed the set C tilde. C tilde is in here. Here is the C, and then we join all the point in C tilde with C. And now it's known that the set B that we obtain with joining all those straight line has the measure 0 in the plane, so it's a set of measure 0, is compact, and it contains a segment on each direction joining the set E tilde with the set E. That means E tilde is the whole interval 0, 1/2. E is the whole interval 0, 1. And when we join all the E tilde with E, we just get a whole, I mean, the number of direction. Well, we get from this to this one, so more than pi/4, and an angle of direction are filled by joining E tilde with E. And the point is that if we join C tilde with Z, we obtain exactly the same number of directions. So here we have a set C tilde and a set C, which are this Cantor set. And it's easy to check directly that these two sets has Hausdorff dimension 1/2. So they are set of points in the line having Hausdorff dimension 1/2. And so the union still has Hausdorff dimension 1/2. So here we have a set of Hausdorff dimension 1/2. And nevertheless, when we join a point in C tilde with the point in C, this direction fill a whole angle, say, greater than pi/4. If we just rotate this construction by angle pi/4, we get the union of 4 of this construction, which has the property that has dimension the union of the CEC tilde corresponding to the 4 rotation has half the dimension and half. And nevertheless, the set of difference contain points which are at orientation. I mean, the direction is every direction in the plane, and the distance between them is between 1 and 2. And then, so this is an example. We show that this theorem here, 3, is best possible. And the theorem is that suppose that we have in R2 a bounded set containing for each theta in the unit circle, so for each direction in the plane, the K contains 2 points, it's called Z of zeta, W of zeta, such that the difference is R theta theta. Theta is a vector, R theta is the corresponding radius, the distance. And then suppose we have a set capital K with that property, that the difference, with the difference we obtain all the direction with the radius between 1 and 2 in this case. And the theorem is that in this case, we have that the dimension of capital K has to be greater or equal to 1. Well, except for one problem. This dimension is not Hausdorff dimension. This is what is called the fractal Minkowski or box counting dimension, which is closely related with the Hausdorff dimension, but it's not exactly the same. But that is all that I can prove. And this is a recent result I have obtained. It's still unpublished, and it's the result I wanted to offer you in this video. But thank you.
Okay. Professor Antonio Cordova, thank you very much for your very nice presentation. Then I invite to all the participants that especially are connected on YouTube to make questions. Remember that you can write your questions in the chat on YouTube. Also, I see Professor Jennifer Agnelli connected, and Professor Cristiana de Filippis. You can unmute yourself, both Professor de Filippis and Professor Agnelli, if you want to make a question. Okay. On the meantime, Professor de Cordova, Jenny says no thanks. It seems Jenny is very happy with the presentation of Professor Cordova. Professor Cordova, I have a question, right? Because there is this old paper by Terence Tao from around 1998, 1989, something, right? That relate different problems in harmonic analysis and geometric measure theory, right? That, for instance, local smoothing conjecture, Wagner's conjecture, and relations between this problem in particular and local smoothing conjecture implying Kakeya conjecture and so on. And then your problem also related with Kakeya. I wonder if are known in your setting relations between these problems or similar problems with this problem that you show us today.
Well, I mean, this, of course, there are similar problems. You may, I mean, the standard Kakeya problem is about needle in n-dimensional space. And so the conjecture is that if you have a set in n-dimensional space that contains a needle on each direction of the space, that set it could have measure zero that we know from the old time of Beshikovich, which is the hero of this theory, as I understand, who built now they call Kakeya set, but I think it should be called Beshikovich set, which is a set of measure zero in the plane, which contain a unit segment on each direction. This is an interesting question raised by Besikovic. He was interested in this question because of the question in Riemann integration theorem. Fubini's theorem worked beautifully for Lebesgue integral, but for the Riemann method of integration in general, Fubini's theorem is false. And the question that Besikovic asked was, given an integrable function in the plane, can we find a system of coordinates? Can we rotate the system of coordinates so that Fubini theorem is called for that function with respect to this system of coordinates? The answer is no. And Besikovic answered the question he asked by building this set. That is a set of Bessa zero which contains a line on every dimension. Now it's called Kakeya set because I think that a couple of years before Besikovic, Soichi Kakeya, in 1917, raised the question of what is the set of minimal area in the plane where we can move a needle to change the position of the end point. That is an interesting question, probably not as interesting as the one that asked by Besikovic, but they are closely related. Kakeya asked that question, apparently from his publication, we cannot infer that they have an idea of the answer. The idea is and the answer came with Besikovic. So, but nowadays it's called Kakeya set, and everybody talk about Kakeya problem, Kakeya set, and so on. In fact, you mentioned that I wrote my thesis in Chicago in 1974, and the title of my thesis was The Kakeya Maximal Function and the Spherical Summation Operator. And in that thesis, I proved an estimate for the so-called Kakeya maximal function. So for an integrable function in Rn, we take for the supremum of the averages of that function over neither of a certain eccentricity, let's say capital N. And the question I solved in my thesis is that in dimension 2, that maximal function behaves very nicely in the space LP from p equal to infinity. And to behave nicely means that it's bounded by a power of log n. N is the eccentricity of the needle of we want the number of directions that are relevant to the problem. That estimate in particular implies that the Hausdorff dimension of a Kakeya set in the plane is 4, is equal to 2. But I could prove it only in dimension 2. In dimension 3, it remains an open problem. It's a famous open problem to estimate the Kakeya maximal function in dimension 3. And very recently, in fact, a year ago, Han Wong and Joshua Thal has surprised the analyst people by proving a weaker version of the Kakeya maximal function conjecture. The weaker version is also very nice because it says that the Kakeya set in dimension 3 need to have exactly the Hausdorff dimension 3. As far as I know, the proof cannot be carried out easily for higher dimensions. So in higher dimension is still an open problem, and even in dimension 3, from the harmonic analysis point of view, the relevant subject is the maximal function, or you mentioned the restriction theorem and all the Wagner reasonability, all these questions which are related to one or the other, and those questions are, as far as I know, open, wide open, even in dimension 3. Okay, so now what you ask, this result I have obtained is has a reminiscence. You have the spirit of the Kakeya
Yes.
problem, but,
Yes, sure.
I can okay, but for cycle in dimension 3, the solution is the sharp solution is the one I presented here. In dimension n, I have this extension, but there is an open problem. Suppose that we are in dimension greater than 3, and we take a sphere as d minus 2. Okay, then
Yes.
then my result is that in that case, if you have a set containing such a sphere on any position in the space, the Hausdorff dimension has to be d minus 1 on that sharp. But you may ask, we may ask, what happened about a set in dimension n which contains a circle, a one-dimensional circle in all possible positions in the space? What is the Hausdorff dimension? Well, I know that if n is 3, the Hausdorff dimension has to be 2, and that's sharp. But for higher dimension, it's an open question. And I would say this open the difficulty of this problem in higher dimension. I mean, in this case, higher than 3, 4 is equivalent, is completely equivalent to the difficulty of the Kakeya problem in dimension higher than 2. Okay, so there is a connection, I would say, in the nature of the question, and there is also a connection in the nature of the proof.
Right. I see. Thank you very much. Yeah, no, just a comment about something that you mentioned, right? It was close to 2020 when Hong Wang and Larry Good from MIT also used your Cordova, that they call Cordova estimates, right? Cordova estimates, square estimates to prove the local smoothing conjecture in dimension 2, right? So interesting, interesting. Okay, Professor, thank you very much. I think we don't have questions of other people in the chat. Our colleagues, Jennifer Agnelli says that the talk was very clear, very interesting. So just thank you very much from the team of ICMAM Latin America on behalf of the team. Thank you very much for accepting our invitation. I'm looking forward to have you in future ICMAM conferences. I'm sure that people have enjoyed your conference. Thank you very much, Professor Cordova.
I'll be glad to be.
Thank you.
Bye-bye.
So actually now then we have a break. We are going to start in 1 hour with the talk of Professor Ingrid Davechis. Okay, so I really encourage to all the people that are following us on YouTube to keep connected and to stay here in 1 hour with, for the talk of Professor Davechis. Thank you very much. Thank you very much, Professor Cordova.
Thank you. Bye-bye.
Really, how they say a considered promise? Is that all right?
Hello, Professor Dabesis. Are you here? Professor? Will you hear me? Hello. Okay, I can see the Professor Dabesis is connected, but
Hello, I'm
okay.
here. Yes.
I'm here? Good, great. How are you, Professor? Nice to meet
Uh,
you.
Good to meet you.
Thank
So,
you for accepting our invitation.
and you can hear me fine, everything, or should I wear headphones?
Yes, I can hear you well, very well.
Okay, no problem.
Maybe could you share your screen to check the...
Okay, so let me try to share.
Yes.
Uh, so, select window or screen. Allow it to share the screen. Yes, it does not turn on. So,
Let me check.
okay.
You are co-host.
Ask to unmute. Okay, I'm now co-host. Okay, let me share.
Yes.
It does not let it the yellow the blue window for allowing to select screen. Okay, so it doesn't light up.
Okay.
It does not light up. I mean, I can click not now, and then it goes away. But so if I click on share, it shows me allow app.zoom.us to see your screen, select window or screen, and it then below it has two buttons. It has not now or allow, and the allow is grayed out, so I cannot click it.
Oh, let me check.
I am on Firefox. Would you prefer that I'm on Google, on Chrome?
Oh, yes, maybe yes, but it's strange because
Let me try to
yes, like you
log out.
prefer.
Let me go to Google to Chrome because this maybe
Okay.
isn't okay. So I'll leave now and I'll come back.
Okay, we will wait.
Professor Daveches is going to enter again, okay?
Yes.
Okay.
Professor.
So let me try
Okay.
to share my screen now.
Okay, perfect.
Choose what I want to screen, a Chrome tab, a window. Okay. So let me, for the moment, let me first put the talk up here. Okay. So can I do this? Share. Yes. Do you see my title?
Good, I can see now.
Okay. And if I go to full presentation, then it's, you see the full presentation, you don't see. Okay. And I can stop sharing. Oops, what's happening? Do I see you now?
No, I cannot see.
Oh, now I can see you. Yes, but I stopped sharing. Do you want me to keep sharing? Or are there still
Yes,
instructions?
yes,
You want
please. Could you
sharing?
share again? And check
Okay.
the pointer.
Okay. I want to share this window. Share. Okay. And then I'll go to full presentation. Okay, do you see my pointer?
Yes, I can see. Could
Okay,
you
that's
try to pass the slide? Great.
okay.
Perfect. It's
Okay.
working. Okay. Okay, we have 2 minutes to
Okay.
start. So I think we wait for the 2 minutes.
Are there questions at the end?
Yes.
Or are you monitoring the chat to see questions? Because I see no chat now.
Yeah, the question will be in the end. I think
Okay.
it's better. Okay, we have Karel with us now. Hello, Karel.
Hello, sorry to be late.
Very good. So
Could
we
you
have
hear me well?
Shall I stop sharing right now?
No, I think it's in this way. It's okay, Professor, because it's left 1 minute
Okay.
to start. Yeah, almost there.
So we have with us Karel and Boxtal, who actually will be a chair of the session of Professor Daveches. Karel is from Belgium. So we
Okay.
found very
Very nice to meet you.
very nice.
Aangenaam.
Maybe both of
Nice
you
to
can.
meet you. Yeah,
Aangename kennismaking.
Okay.
You hear me?
Yeah.
Yes.
Everything's fine. Okay.
So maybe
Perfect.
Karel, you have 1 minute left just to.
Is it already live on YouTube?
Yes.
Yes.
Yes. Thank you very much, Karel. So we leave you
Yeah.
with Professor
Welcome, Duvan.
Davechi.
Okay, I think now we can start. So go ahead, Karel. Thank you so much.
So, hello everyone. It's a great pleasure for me to introduce our next speaker, Professor Baroness Ingrid Debouchy. So, Professor Debouchy is one of the most renowned and influential scientists in applied mathematics and engineering. Currently, she is James Duke Distinguished Professor Emerita of Mathematics at Duke University. And in 1980, she pioneered wavelet theory by developing Debouchy wavelets, a breakthrough that transformed harmonic analysis, signal and image processing, and laid to the mathematical foundation for the JPEG 2000 image compression standard. So most recently, and also recently at Ghent, Professor Debouchy received a honorary doctorate, and there she was giving a presentation or demonstration about how mathematics can contribute to the preservation of cultural heritage together with collaborators, she developed image processing techniques that support the restoration and analysis of a masterpiece, well-known one, the hand altarpiece, The Adoration of the Mystic Lamp by Hubert and Jan van Eyck. Her scientific achievements have been highly recognized by numerous prestigious awards. I will only mention a few recent ones. In 2023, she received the Wolf Prize in Mathematics, when she was the first woman to receive this distinction. Most recently, she got in 2025 the National Medal of Science, and this is one of the highest scientific honors in the United States. So today, Professor Debauchy, she will speak about discovering low-dimensional manifolds in high-dimensional data. So in this lecture, she will show how diffusion-based methods can uncover hidden geometric structures in complex data sets, and how these ideas can be applied to problems in biology. So Professor Debauchy, we are delighted to have you here with us. And, please, the floor is yours.
Thank you so much, Karel, for this introduction. So here I go. Very often, I mean, and this is caricatured by this little figure here, data may be sampled from a manifold or a variety that has a smaller dimension than how it is presented at first. So, for instance, if I wanted to sample points on this blue surface, then it's really a two-dimensional object, but it's embedded in 3D. It might not know the parameterization that gives it its true dimension of 2 dimensions. So, how do I discover it? Well, I like to think of an analog with the little sequence on these toy animals. Each of them are just little flat discs, and their collection really follows very nicely that surface. And so the collection of small discs at every place on the surface gives you an idea of the surface. And that's really what we're going to do. If we imagine a small collection of neighbors on each of these, then we can look at many little patches, and this is still a little curved patch on the surface, but we can approximate it very well by a little tangent plane at its center, which would give us a sequence. If we had all these little tangent disks, then we could imagine doing a diffusion from disk to disk, and that way walking on the surface. And so if we have this big data set and we'd like to walk on the surface, the diffusion operator will tell us, if we do look at this integral kernel, will be able to tell us about the geometric properties of the data set. Then we can walk from one point to a remote point by hopping small distances on the data set. Small distances, small hops allow us to move to a neighboring point that is near another little disk and another little disk and so on. And that allows us to then make a long path along the surface. So computationally, we are going to do something very we're going to use some approximation. So in first approximation, if you have a manifold and you look very locally, then the distance between 2 points that are near each other on a manifold is in first approximation the same as the chord in the ambient direction. So in all the dimensions that are given to you, and which may be much more than the true dimension of the manifold. And it's also in first approximation the same as if you pulled back the surface to the tangent plane as the distance between the correspondent point on the tangent plane and the point on the manifold. So that's one thing. The second thing is that if we want to write a diffusion kernel, then the diffusion kernel on the ambient space has the same shape as the diffusion on the tangent plane. We don't know the manifolds, we don't know the tangent plane, but we do know what the kernel looks like, because in Euclidean space, it does not depend on dimension except for normalization. So given data points, we'll, and hoping that we have a way of characterizing distance between those data points, a dissimilarity, we hope that locally this can be represented as being in a Euclidean space, and we can look at a diffusion operator that is given by the traditional kernel in a Euclidean space, namely e to the minus distance squared over 2t, where the t is the extent of the diffusion time that we are using. The normalization factor that we see here, that I'm circling with my mouse, is dependent on the dimension as well as on the dimension of the manifold, and will also be influenced by the fact that I have to take care of the fact that I'm not looking in a continuous space. Well, I'm looking in a continuous space, but I'm going to sample it discretely. So we want to choose this time t very carefully, because it needs to be sufficiently small, because otherwise we'll diffuse largely. We'll look, for this distance squared, we look at the distance in the ambient space. So we use Euclidean distance, and we know that we cannot trust large distances. So we need to make the distance sufficiently small, and we if you then want to diffuse further, you want to, so diffusion by this small time t is like diffusing on one of these little patches. You, if you look at the operator repeated many times after itself, it's like diffusing a little bit and then diffusing another little bit, diffusing another little bit. And the operator itself will take care of linking the patches with each other, since it is a small local operator, but with little spread. And so powers of it will be enabling to look will implicitly look at longer paths. Now, normalization, we need to normalize this operator. Well, heat diffusion on a manifold really is the operator minus Laplacian, exponential of minus Laplacian t, defines a random walk. So that the approximation that we built from the data, which are sample data, should do likewise. So we are going to posit that the discrete approximation that we take, when we sum over the columns, should sum to 1. And so I can then normalize by computing the what the matrix without its normalization, when I sum over the J index, the column index, gives me. And I can renormalize by multiplying with a diagonal matrix that inverts that sum. So this WT matrix will now have normalization where each column sums to 1. In fact, it turns out that an even better normalization is something where you try to normalize in both ways so that you are symmetric as well. This matrix is not symmetric. But now, how should we pick t? I already said that we want to pick those diffusion times, not too large and not too small. And it used to be that this was more of an art than a science. And my graduate student, my then graduate student, now a professor in Copenhagen, in Denmark, in the University of Southern Denmark, Shan Shan, found in her thesis a very nice principle. After all, we have built something that we hope will have sufficient similarity with diffusion that we can obtain some geometrical information about the whole manifold from applying this operator. Now, a diffusion operator is an operator that the operators form a semigroup. So what that means is that we want the product of WT, WS to be close to WT plus S, or WT squared minus W2T should be small. We know that if we pick our T too large, our approximation, the approximation that we built from data, will not be trustworthy. So what we can do is we can look at T values and increase them until this error gives us a wrong result. So let's look at a couple of benchmarks. So this is a helicoid. So it's a helix wrapping around a torus. And the blue and red are just shown here in order to give you a good three-dimensional impression, which you wouldn't get with just black points. It is a one-dimensional thing that lives in 3D. If you apply the diffusion operator, and I'll come back to how we do this, and then try to find out the implicit dimension of this manifold, what you find is that you have different realizations. This is for a very small t. The one in the middle is for a t that is a bit larger, and the one at the right is for a t that's even larger. You see the one at the right, t has been chosen too large. And so some of the toroidal, some of the fact that distances are smaller on the inside of the torus and on the outside of the torus has been inherited, has been felt. This is not an inherent thing. What we really want is that circle. If we don't diffuse far enough, then the gaps between data points start showing us something, and we showing up, and we don't get a good impression of the manifold. But if you look at this, so 2 slides ago here, we looked at this this proxy for measuring how well the discrete WTs are having this semigroup property, then you see that this semigroup error is smallest for the case that is indeed corresponding to what on this benchmark example we can verify is the best choice. Another one is the Swiss roll. Again, here are different embeddings that you get for different choices of T. They again correspond, the one that best corresponds to what we know is the ground truth, a rectangle, corresponds to the best the smallest semigroup error. So that gives us a rule of thumb for choosing T. Okay, so I have told you, I've sketched to you how we can build a matrix. We have normalized it correctly. Now what you can do is, we have chosen the right T. We can look at its spectral decomposition. That's to say, we know that this has in this case, the non-symmetric one, in fact, one of these two vectors should have a tilde because it's not a symmetric operator, but it's similar to a symmetric operator, so I can decompose it. And if I then look at a large diffusion, all that means is that I have to look at the eigenvalues with a larger exponent. The T here should also have had an index L. I apologize for that. So this is a WT that depends on L and on time. And if I take different powers, then I'll be looking at a much longer time than the little time for which I did. But when in practice, what I will do is I will trust only a certain number of eigenvectors, because the higher I go in the eigenvector index, the more influence the noisiness of my sampling will give me. So I'll typically truncate at some capital L. I take the WTL, take them to some power lambda, and look at the values of psi L in each of the data points. And so I parameterize my data points in this way. And I can use that to define a distance then in this new parameterization. Again, the WT here should have an L index, gives me a diffusion distance. This concept was introduced by Ronald Koifman, Stéphane Lafont, and also Mauro Maggioni, and has been used extensively in a large number of applications. It's also a a version of diffusion distance of Laplacian distance introduced by Belkin and Yogi. By looking at diffusion rather than Laplacian straight away, you get a better impression of the larger distances automatically play a lesser role. I'm going to talk here of an application of this idea to data set of biological shape and define an additional extra layer to diffusion methods that I think is applicable to a wide variety of settings other than these biological shapes. So let me first talk about the biological shape. So it started by a conversation at a meeting of scientists from many different directions. It was a social event with biologists. I mean, Jukka Jörnvall is a very distinguished Finnish biological morphologist working in paleontology. Doug Boyer was then his postdoc and is now a full professor at the University of Duke University. We ended up at the same place, and of course that helped with our collaboration in the biology department, in the evolutionary anthropology department. And they studied teeth and bones of animals that still live, but also that are extinct in order to understand evolution. And I'd like to show you many collaborators, of course, Doug, but also many people who have over the years been students or postdocs with me and who have gone on to distinguished career. Rima El-Afari is now a professor no longer in Zurich. She's in Aachen. Jeroen Lipman is a professor in Weizmann. Shanshan, who I already mentioned, is in Denmark. Shahar Kowalski is a professor at University of North Carolina. And Shara Feigenbaum, with whom I'm still working on, was my co-author on a review article that describes many of the features of today's talk. Okay, so the first thing that they asked us was a project where they wanted us to quantify the complexity of teeth. So Jukka Jörnvall told me that they had found a very nice way of characterizing the complexity of the chewing surfaces of molar teeth of mammals by means of looking at that chewing surface and seeing how complex it was. And in practice, what they did is they used a very ad hoc method by taking screenshots of visualizations with in computer graphics of the surface and looking at changes of color in those visualizations, which essentially were measuring the change in angle of the normal to the surface as one moved over the surface. So Jeroen Lipman, who was done a postdoc with me, liked to knew many new tools from a discrete differential geometry in order from computer graphics to implement this, and this gave rise to a new tool that turned out to in increasingly better implementations to do things very robustly. We'll come back to that at the very end of this talk. But after that, they asked us to do something much more complex. They said, well, can you find an automatic way to compute the procrustes distance between two surfaces without landmarks? And let me clarify what all this is about. So the data they use are data often of very small primates. So these are, they micro CT scan the teeth or impression of the teeth and then extract the surface. Now, you could say, of course, teeth are three-dimensional objects and they have internal structure. Why don't you use the three-dimensional? Why do you try to get only the surface data? It's because for many of the samples, we don't actually have the teeth. We have just high quality impressions on dental resin resin of these teeth. When Doug Boyer visits collections anywhere in the world, if he travels for his job or for field work, he tries to always, of local collections, get as many permission to take as many impressions of their precious rare fossils as he can. So he can bring back those impressions from which we can get the surface data, but not the three-dimensional stuff. So that's why we work with the surfaces. So once you have these, you do a micro CT scan of these, you can then extract surfaces and you can parameterize them or what is done in order to compare in a whole collection of teeth to quantify which ones look more similar to each other and different from others. Experts typically look at the collection, look at features that they know are essential in the teeth morphology and that they have in common, and they put landmarks on all these points. They label them. They label them on the whole collection, and they then use the spatial coordinates of these landmarks as features. So if they take K landmarks, then they will have 3K numbers, and they will then represent a shape. This R3K numbers, this vector in R3K is a representation of the surface as a proxy. And here you see a whole lot of teeth that have been landmarked similarly by experts. And what then is used in order to, the progressive distance is then given between two surfaces, is then given by looking at all the points on one surface. Here, xj is now all the points from j equals 1 to capital J are the three-dimensional vectors on one surface, and the yj are the three-dimensional vectors on the other surface. And we then look the best possible way of moving one K tuple to near the other by a rigid body transformation, so rotations and translations, and the sums of their squared distances after this transformation is a progressive distance between two surfaces. So now landmark placement is tedious and time-consuming. I mean, it needs people who have training on marking these, and then also, as we need the same number of landmarks on all the surfaces that we're going to compare, if the fossil happens to be missing a piece, then that means that we cannot use the corresponding changes of shape in the rest of the collection between teeth because we can't put a landmark there. And debates sometimes exist even among experts on where to put landmarks. So what they asked us is saying, look, these progressive distances, they work well for when we want to do a study of what areas of teeth have been more subject to ecological pressure in the evolution of the different species than others and so on. Can you find a way to compute something mathematically without landmarking, as that does as well as what progressive distance does for us? And well, the surfaces they have in very, very fine resolution. Typically, we have to subsample them. And okay, so what we did then, and this is a collaboration that started about a little bit more than 15 years ago. So the work here, what I'm reporting on is that first work. We defined two different distances for them. One was very nice. It used optimal mass transform and conformal flattening. We really liked it mathematically. And the other is what we call the continuous progressive distance, which I'll also define. So the first one, so if you have two teeth, we wanted to make the search easier I mean, surfaces in 3 dimensions are not as easy to deal with as when you flatten them conformally. Since these were surfaces that had no holes but a rim, they can be conformally flattened into a disk. And the one that has a conformal factor that measures at every point at the disk how much distances had to be shortened or lengthened in order to make that flattening possible. So the inherent geometry is still encoded in this, this landscape on the disk given by the conformal flattening. In order, we wanted to define a distance via mass transport. So then you have to find, for points in one and in the other, some way of comparing the geometry between them. Now, since we were looking at conformal structures, obtained with conformal flattening, and the conformal flattening is not unique, we could, for each of these 2 points, in order to compare them, have looked at a conformal flattening that would have placed those 2 points in the center. And then, since we wanted to compare locally their geometry, we could look at little disks around them and compare how the conformal factor on one little disk compared to the other. And that's how we defined a distance between the two based on that radius. And we can look at the square or look at the distance here. I put the first power, but that's not really essential. We might look at the square too. And then you can look at the Wasserstein distance. In order to find the optimal given 2 conformal factors, what is the best way of defining a combined measure that minimizes an integral of that distance. So we call that the conformal Wasserstein neighborhood distance. Then we also, it turned out that this worked well, but that was not, was slow. So we also defined a continuous Procrustes distance. And so again, the idea was you first we had to in the Procrustes distance, what the biologists give you is something that is landmarked. So they have identified a few points and other points, and they know which points correspond to what. Remember the coloring we had on that diagram. So if you had a correspondence map between the 2 surfaces, then you could try to look at a distance by taking the infimum over all rigid transportations of rigidly transporting X and comparing it where the correspondence makes X land. And so on this little diagram below here, I started with something on the structure on the blue, a sampling on the blue curve. And I had a correspondence with the red ellipse, and we were looking at the sum of the squares of the distances. But if we rotate it, then we got a much better and smaller integral. But in fact, that is the smallest we would get for this correspondence map. But one could find a different correspondence map that would even do better. So if you want to minimize over the correspondence maps, you need to know a class of maps in which you work. And we chose to define it as the area preserving diffeomorphisms. Now, that of course, there's no reason at all that the biological correspondence would be area preserving. However, in practice, the biologists were happy with the idea that you would start on one tooth and try to put 500 points down and have them well distributed. Now, well distributed means that each one has about the same area around it as that is of teeth, of points of the tooth around it as every one of other of them. So in a certain sense, you look at your surface, you look at your sample points, you can look at little Voronoi cells around each of them. The piece of tooth that is closer to your sample point than to any other sample point, and you can look at that area. And saying that your 500 points are well distributed means that each of them has about 1/500th of the surface in its little Voronoi cell. And then you take another tooth, you put 500 points down, and you try to match points to each other, and all of them represent really the 1/500th of the area, and the areas of the teeth have been normalized to 1. So what you're really trying to build discretely is something that is area preserving. Now, this is only an approximative distance, and we'll see that we will move away from area preserving. But in order to define the mathematical distance, we looked at area preserving. In practice, actually, because the area preserving diffeomorphisms are very difficult to search, we proved that if that distance, this progressive distance, is small, then the minimizing area preserving diffeomorphism is very close to the minimum conformal map. And conformal maps are easy to find because for that you just do conformal mapping and a conformal flattening and look at Möbius maps. So this is to define the thing nicely mathematically, and so that you can prove theorems with it, and to also have something that corresponds to computational reality. So, okay, so we have defined now our continuous progressive distance. So I've defined to you 2 distances now. One that corresponded to the conformal flattening comparison of neighborhood geometry via optimal mass transport, which we call the conformal Wasserstein neighborhood distance, and the continuous progressive distance. Now, once you started comparing, so here in these diagrams, what I'm showing you is a color representation that compares with dark blue being very small, going then over white to red, which is larger. The ODLP, observer determined landmark placement distances, so with the distances that we gave. So for each pair, IJ, JI and IJ, you see on one half of the triangle what the biologists gave, and on another half of the triangle our distance. We had labeled the samples so that things that were very similar had labels close to each other. What that means in our terms of trusting small distances more than large is that we would like our computational distances close to the diagonal to be very similar to what the biologists gave. And you see a reasonable match. But it's clear if we start looking at this picture that in fact the continuous progressive distance did better if you look at these 2 zoom-ins than the conformal Wasserstein distance. So even though it was a mathematically more sophisticated object, it turned out that the continuous progressive distance, which was also faster to compute, led to better results. Okay, so but that's just distances, the conformal. So here in this graph on the left, you see the result of the multidimensional scaling, so the best possible 3-dimensional projection of the distance map we obtain with the continuous progressive distance between among a collection of 50 different teeth, primate teeth, which belong to 10 species for each of 5 genera. And so that's why you have 5 colors. Within each color, within each genus, we use the same color. And the biologists were actually relatively happy with the clustering that seems to happen in this picture. We were not. But then we used on those same data, now we used those data to think of it as something where we had a similarity distance, and we could use that dimensional picture, that diffusion distance stratagem that I explained earlier. And when we did that, which is just the idea that you want to understand the geometry of the understanding collection, which you believe to be much smaller dimensional than, well, the way you had sampled it, 500 points per surface, three space coordinates, that's 1500 dimensions for every one of them. So the way of trying to get the underlying geometry better through diffusion gave then in diffusion distance, which we defined earlier, this picture when you tried to find its best three-dimensional representation, in which the species cluster much better. And this is where our work stood about 10 years ago. And then came the work my then graduate student Ting Ran Gao realized that you could do even much better. And in fact, I'll show you how the picture on the left was obtained from, again, the same samples and data set. What he said, what he realized was we used the local distances. That's something you always do in the, and you knit them together. You knit together all these little neighborhoods in order to define a diffusion that then via spectral parameterization defines you that distance. But we had given up a lot in doing that. I mean, yes, if this collection of teeth was given, then in order to define that procrustes distance, we also defined first a correspondence map between them. That was the minimizing map for the procrustes distance. And we used that to find these numerical values, but they could do much more for us. In fact, if you think back of this picture, we believe that there is a manifold, something that has low dimensional structure on which all these teeth live. We have no idea of its geometry, but we try to probe it. But at each point of that, on that manifold, we have not just a point, we have a two-dimensional surface. So we have really a fiber bundle. We have something that has, we believe, to have a manifold structure. And for each point, it's like having a hair. I mean, except it's a two-dimensional tooth, but on it. And we have correspondences between them. So we have what differential geometers call a fiber bundle and a connection on it. So, and he used this to define a much more detailed diffusion structure on the higher dimensional object. And then only at a much later study, a stage in the mathematical model, did we project down to find horizontal diffusion. So a little bit on fiber bundles and so on. A fiber bundle is something where you have a base manifold given in these examples by a circle. And for each point on the base, you have a fiber. All these fibers are really copies of the same fiber manifold. But for each locally, you can nicely project down from the fibers down to the base, and you have locally a kind of product structure. That product structure need not be true when you look at the whole thing, as illustrated by the fact that the Möbius band is not the same as a cylinder. Mathematicians like to look at many geometers at many different fiber bundles. Here, for instance, I have unit vectors in the tangent bundle of this circle. Here I have another another vector of tangent bundles. Well, no, sorry, these were tangent bundle. Here were unit vectors in the tangent bundle. Here I have another selection of tangent vectors. And you can then, we were looking at the diffusion operator. We were looking at mappings, trying to get an idea of mappings on the base manifold. But in fact, we do have mappings that between the fibers and these mappings between the fibers, each of them for each point here give us a copy, give us an idea of what the diffusion could be on the base manifold. And the way that was then implemented by Tingran is that he looked at the collection of all the teeth together and all the sample points we had on the different teeth. And now it wasn't even necessary for us to have an equal number of sample points on all the teeth said in passing. And he looked at a diffusion where you would diffuse on the teeth and also diffuse among the teeth. So a little kind of Trotter product formula of diffusion on that whole enormous manifold, and looked at the dominant eigenvectors. And here, every eigenvector would have values on all the teeth, which are indicated here in different colors. And the fact that we have a shorter stretch of orange is an indication that we might have fewer sample points on the second tooth than on the first, for instance. And then you can do many things. The first thing he did was you can, in this enormous space, because you have points on each tooth and you have all the teeth together, so this becomes an enormous space, you can say, after I have reparametrized, so used the eigenvectors and the eigenvalues and look at them at a reasonable power of the eigenvalues, I can try to, in that parameterization, cluster. And this is what you get, for instance, when you cluster among our 50 teeth in, I think, 13 clusters. This was already used by the biologists when they saw this, because it's what is very interesting is that, first of all, every cluster is represented on every tooth. That was not necessarily a given. But the areas that belong together are not equal in area. The zones that belong together are not equal in area. So there are places where this turquoise zone is much smaller, for instance, than on other teeth. And even though we started the whole structure with a continuous progressive distance, where the correspondence maps were area preserving. But remember, we only trust them when things are very similar, when distances are very small, and they have enough elbow room. There's enough in this reparametrization, they allow for a correspondence that's more flexible. So that was the first application. We had done it just for a sanity check, but we were happy that the biologists even found that picture useful. The next thing, remember I said we're going to keep the mappings inherently, that we defined correspondence maps alive and for our analysis, but then project down on lower dimensions at a later stage. And that we do by taking the restriction of the eigenvectors to each tooth. This was an interesting idea that we have not fully understood geometrically yet, but the restrictions to each of the base manifolds, to each of the fiber manifolds. And we can then look at these vectors and look at their little gram matrix. We normalize them and so on. If two teeth here were identical, then we would find eigenvectors. They would have the same copy of eigenvector, and we would find that the two matrices, the gram matrices of their restrictions, would be identical. Of course, they aren't, and so. But this tells us that if what we can take as a proxy for similarity between the distance between the surfaces, the difference between these matrices. So these are now small matrices. We take k eigenvectors in total. These are k by k matrices, and we can look at their similarity. And that is what Tingran used. So the same analysis that had given to these diffusion distances, but where we had not preserved the maps to compute the diffusion distance, but by preserving the maps and then do the analysis I just sketched, gave rise to this base diffusion distance on the manifold. So we were using much more of the correspondences than we had before. The interesting thing is that this clustering had a biological content. Not the evolution of I mean, look, we're looking at teeth only. But it did cluster together. So you see the purple and the blue are in fact the furthest related of these species, but they're both frugivores. And the two folivores were clustered together. And the Chimera, the insectivore, was separate. So there was biological content in what we found. And that's what we don't want. I'm showing these diagrams not because I believe that one should do clustering of animals, that one should identify from their teeth what animals eat. Biologists have other ways of doing that, or that one should identify species by our methods. What we seek to do with this is to always check that we have preserved biological content in our analysis. Another thing that you could do is look at the dominant eigenvectors and look at, that gives you 3 values. Let's look at the 3-dimensional representation we get for each of the teeth. And the interesting thing is that, well, you get a 2-dimensional surface, but that's not surprising. There are 2-dimensional surfaces. If you had a parameterization for them in which all of a sudden they were not 2-dimensional surfaces, you would know something was wrong. But we get the same 2-dimensional surface. If you, so what that allows you to do is to re-register. Because of course, if you look 500 points, 500 red points, 500 blue points, and so on, they're not going to be truly correspondent. So, but what you can do is now see, oh, look, this blue point here is really in this triangle of red points. And so you can find the true corresponding red point for a blue point. And so we actually did that. And here I have shown, yeah, so it's more clearly see. I asked students to point out on landmarked, so things where we had found a correspondence map, how would we re-register? And I asked students to highlight the points for which this made the biggest difference. And when I showed to the biologists what this method was doing, they agreed that the direction in which we were re-registering was exactly how they would have tried to correct the assignment of the points. So other things. So I'm getting now to much more recent work. With our re-register method, I mean, we now have, so this is actually one tooth by itself. There's a method in statistics that's called Kriging that tries to sample in a data set where you learn the most from finding a sample. So you have many different, you have a collection of similar things. You look at locally where things vary the most, and you will always try to sample where there's most variance, because there you learn the most by taking a sample from one particular population compared to others. So if you do that, if you have your whole collection of teeth, and we have looked at the map that we get from our diffusion, then you can look at where would I learn the most if I sampled. And this would be your first sample point, the second, third, and so on. So you see how a method like that is already singling out very interesting points on the tooth, comparing it so this is Gaussian process landmarking, comparing it with local maximum of local curvature, doesn't do as interesting. Or the geodesic farthest point sampling, that is the most spread out sampling that I described earlier. Even more interestingly, when we look at the full collection together and we say, let's now sample on the whole collection, let's try to find not just for one tooth where we learn the most, but where would we on the register, that's one, where would we pick the point and immediately look at its correspondence point everywhere. It finds points that our collaborators are very excited, seem to get close to what they would call automatic landmarking for the whole collection. So we are finally getting close to an answer to the question they asked us at the very beginning. And so here are some of those very recent results. We want to use a local geometry adapted version of the progressive distance, where we take into account not only the distance, but also in the feature vector for which we compute correspondences, we also want to take into account the local curvature. And I told you we had this beautiful way of using differential geometry in order to define local curvature. Here is a robust implementation of Dirichlet normal energy computation, not just for teeth, but also for shells and so on, which has been beautifully tested out and is very, very robust, more robust than algorithms we were using at the beginning, to give us a kind of curvature, scalar curvature field, the Gaussian curvature on the teeth. And then we want to ultimately, we're right now trying to find the best way of really finding the two-dimensional template fiber in our fiber bundle. After we found the correspondence, what we want to do is in our diffusion, which is a combined diffusion over each of the fibers and then among fibers, we want to play on the difference in diffusion, possible strength between the two diffusions, so that we then get a better reading from the eigenvectors of the base manifold than we at present we diffuse quite heavily over the base manifold and more slowly on the fibers, so that we learn the fibers better. But we want to become more local in our diffusion on the base manifold. And that we hope will also lead us to bring to situations where we will be able to look at not just oops, I don't seem to have my meeting anymore, so I hope you can see me now. But that will give us ultimately an idea of the manifold, not just for species that are very closely related to each other, but also for species that are further removed and for which we can't expect that the correspondence is commutative. If you have species that are very closely related, then you probably have a joint mapping from each to the parent, and that means that locally, since you can always go back to the parent and come down again, all those mappings should commute with each other. Going from A to B or B to C or C to D, if you go to the ancestor X, then you could go to A to X and X to B, or A to X, and then X to C. And so all these things should then commute. If you have a more distant ancestor, then that no longer will be the case, because things will have had time to develop that are present in some species and not others. And so we need to be able to understand better where to coarse grain on the base manifold and where to fine grain. And that's our next step. And that's everything I wanted to say.
Oh, thank you, Professor. I think, Debussy, thank you for this impressive talk. Yeah, I hope the sound is working well. Are there questions on YouTube or from the audience who have followed the presentation on YouTube? Not at the moment. Professor, I was wondering, in the beginning of your presentation, you discussed the local effects of the diffusion operator. Have you considered non-local operators, like fractional Laplacian or nonlinear operators? Can this have applications in this?
Well, the fractional Laplacian, in principle, so we definitely we are using what we want. We want to get an idea of the global geometry, but by using operators that, as you say, the Laplacian is local, but diffusion itself is not really local. It actually, the eigenvectors immediately are eigenvectors, well, that's true for the Laplacian too, but that live on the full space. So you really are trying to knit together, but by combining something that uses only local information, because when you are looking at this unknown manifold, you typically really trust only similarities between things that are very close, because there it intuitively is easier to quantify that these things are closer to each other than either is to that thing. I mean, if you go too far on the manifold, things are so very different that it's hard to quantify that. So that's what I like about these diffusion methods, that they and I think we also implicitly exploit the fact that the heat kernel has the same shape in all Euclidean spaces, and which is a very nice property. Now, there's no reason, I mean, we could use other operators, and in fact, people do use, I mean, in machine learning, people do use Hamiltonian operators and semigroups generated by other Hamiltonians in order to deal with various kinds of problems. I do think it is important to build whatever operator you build as something that is nicely, that you can nicely build as an integral operator on neighborhoods, and then from there build the whole thing. I don't know whether I'm making sense, but
yeah, thank you for the explanation. I was also wondering about you scan the surface with CT scan.
yes,
I think how maybe in some situations there can be noisy measurement or very noisy measurements.
Oh, they are, well, what happens is these are, so they have very, very clean impressions on resin of these teeth. And then they scan this resin, so these impressions, and in air. So as they have a fairly clean way of doing the micro of getting micro CT data out of those. they now, of course, they're never perfect, and so you get this point cloud, and from there you try to get a surface by triangulate by finding the best triangulation that will fit through these. They use various existing graphic packages in order to do that. We also have a way of which I didn't present, but of just going from the point data, the clouds, the point clouds themselves without triangulating, and defining a distance to, I mean, trying to from that point cloud find the closest manifold surface, and then use that for the analysis. We try to build the analysis so that it is very modular, and so that at any point, if a better way of finding surface extraction is done, or a better way of getting a distance with which the rest of the analysis is gone, that can be slotted in, and we still then have the correspondence maps and but yeah. Also, in all this, we should, and we haven't yet, we should really build ways of making error bars. That's to say, we have done for rescanning the same surface, or choosing a different collection of 500 points, choosing them randomly a different way, and then looking at how that affects the results. And we check for robustness that way, but we probably should do it for more things.
Okay, good. Thank you very much. It seems there are no questions yeah, in the YouTube chat, so I think we can finalize today's session. So Professor Debussy, we were very happy and delighted to have you with us, and we would like to thank you for the nice presentation. So
Wow.
tomorrow morning, the program will continue at 7 in the morning in Colombia. So it will be 2 in the afternoon. So afternoon in Europe. So it's 1 hour earlier than today. So we thank all presenters of today, and also the participants, and we hope to see many people tomorrow. So thank you.
Yes, thank you, Karel. Thank you so much again, Professor, for your impressive talk. It was a really pleasure for me. Thank you for everyone who attended the talks today. Like Karel said, tomorrow we start 7 a.m. Colombian time, and 2 p.m. Central European time. And also, like today, we will share by email to connecting by YouTube, okay? 15 minutes before the first talk starts. And you can find also the link on website, ICMAM Latin America website. So thank you so much, and see you tomorrow.
Bye.
Bye.
Oh.
Thank you, Karel.
She left already. Okay. Well, it was she was in Ghent for honorary doctorate. We haven't spoken with each other, but I was in the audience, and there she was speaking, presenting about this removing artifacts. So it was also very nice work, and this is also long-term work for 15 years.
Yeah.
Very nice.
Okay. Thank you. See you tomorrow.
Yeah, see you tomorrow. Bye.